He barely opened textbooks. While his classmates pulled all-nighters in the MIT library surrounded by towers of notes and highlighted pages, Richard Feynman was playing bongo drums in a jazz bar. He'd show up to lectures late, sometimes not at all. His study group? He didn't have one. And when the Putnam exam landed on his desk, the exam that made valedictorians cry and reduced straight-A students to the puddles of self-doubt, Feynman finished in half the time with a perfect score. His classmates, the ones who'd sacrificed sleep and sanity, who'd memorized every formula and filled notebooks with practice problems, most of them failed. Something was deeply, fundamentally wrong. Not with Feynman, with everything they believed about learning. This comes directly from Feynman's own accounts in Surely You're Joking, Mr. Feynman, and verified stories from his years at MIT and Princeton. The details that follow aren't motivational myths. They're documented patterns from one of the 20th century's greatest physicists. What Feynman discovered about learning at 19 would take cognitive scientists 4 decades to prove. But he knew it the moment he noticed something strange about the students around him. MIT in 1936. The physics building at 2 in the morning. A dozen students hunched over problem sets, their eyes bloodshot, their hands cramping from hours of calculations. They'd been there since dinner, some had been there since lunch, and they were stuck, genuinely, desperately stuck, on a problem their professor had assigned that morning. Enter Feynman, strolling in around 2 a.m. after a date, whistling something off-key. He glanced at the blackboard where they had written the problem. 30 seconds of silence. Then, "Oh, that's just..." And he walked to the board, wrote out the solution in 4 lines, and walked out. The whole interaction took maybe 90 seconds. The students stared at the board, then at each other. Then one of them, a guy named Welton who'd spent 6 hours on that problem, said what they were all thinking. How is that possible? They concluded Feynman was a genius, a freak of nature, someone born with a brain that worked differently. They were wrong, but they wouldn't realize how wrong until much later. Because what looked like effortless brilliance was actually something else entirely, something that made Feynman uncomfortable when he first noticed it in himself. Here's what actually happened that night. Feynman had seen a similar problem 2 years earlier. Not the same problem, similar. And back then, when he'd first encountered that type of physics problem, he'd spent hours not solving it, but understanding it. He'd drawn pictures. He'd made up a story about balls rolling down hills. He'd explained it to his younger sister using oranges and a ramp made from a textbook. He'd broken it down until a 12-year-old could grasp the core concept. And now, 2 years later, when a variation of that problem appeared, his brain didn't have to work hard. The pattern was already there, built into his intuition. But what nobody knew, including Feynman himself at first, was that his laziness was actually the most effective learning technique ever documented. He just thought he was being efficient. The real revelation came during a quantum mechanics lecture in his junior year. Professor Morse was explaining something called the Dirac equation, one of the most beautiful and confusing pieces of physics ever written. Feynman copied the equations into his notebook like everyone else. He followed the mathematical steps, and at the end of the lecture, he understood nothing, not a single conceptual thing. He could manipulate the symbols, sure. He could plug numbers into the formula. But if someone asked him what the equation actually meant, what it was saying about reality, he had no answer. This moment, this specific moment of confusion, was where most students shrug and move on. The exam only asks you to use the formula, not understand it. So, why waste time? But Feynman felt something else. Excitement. Because he'd just caught himself doing the thing he hated most, pretending to understand something he didn't. That night, he went back to his dorm and did something strange. He took out a blank piece of paper and tried to explain the Dirac equation to an imaginary freshman who'd never taken quantum mechanics. He got about 2 sentences in before he hit a wall. He didn't understand what spinor meant. Not really. He'd memorized the definition, a mathematical object that transforms in a particular way under rotation. But that was just words. He couldn't visualize it. He couldn't explain why it mattered, so he backed up. Way up, he started with, okay, what's an electron? And then, what do we mean by spin? And then, why do we need this mathematical machinery in the first place? Each time he hit something he couldn't explain simply, he'd stop and wrestle with it until he could. This took him 8 hours, for one equation. His roommate thought he was losing his mind, but something happened during those 8 hours. When Feynman finally understood the Dirac equation well enough to explain it simply, he noticed he'd learned 5 other things he hadn't intended to learn. The foundations he had had to rebuild to understand spine errors gave him insight into problems he hadn't even encountered yet. It was like strengthening a muscle you didn't know you had. Suddenly, other movements became easier too. But this created a problem Feynman didn't expect, because once you know what real understanding feels like, you can't unknow it. And most of his education, most of everyone's education, suddenly felt hollow. He started noticing it everywhere. Lectures where professors define terms using other undefined terms, creating circular nonsense that sounded profound but meant nothing. Textbooks that presented formulas without derivation, expecting students to memorize the result and move on. Study groups where people quizzed each other on facts without ever asking, but why is that true? And worst of all, classmates who could ace exams while having zero intuition for the actual physics. There was a guy in Feynman's differential equations class who could solve any problem the professor assigned. Any problem. He had perfect technique, perfect notation, perfect grades. Feynman asked him one day, "What do you think a differential equation actually is? Like, what's it doing?" The guy stared at him. "It's a relationship between a function and its derivatives." He was quoting the textbook definition verbatim. Feynman pushed, "Okay, but what does that mean? What's it modeling?" Silence. Then, "Why does that matter? We just need to solve them." That conversation haunted Feynman, because this guy wasn't stupid. He was technically brilliant, but he'd learned a trick without learning the thing. He could perform physics without understanding physics. And the terrifying part? The education system rewarded him for it. Perfect grades, scholarship offers, professorships in his future. Meanwhile, Feynman, who spent half his time staring at walls trying to visualize what equations actually meant, was considered lazy by some of his professors. And then something happened that almost derailed everything. A professor called him out in class. Feynman had missed the previous 3 lectures because he was stuck on a single concept from 2 weeks ago. Something about tensor notation that didn't make sense. The professor, irritated, asked him to solve a problem on the board. It involved the exact notation Feynman had been wrestling with. He walked to the board, stared at it for a moment, then said, "I can't do this." The room went silent. Someone whispered, "Feynman can't do it?" The professor, sensing an opportunity to make an example, said, "Perhaps if you'd attended the lectures, Mr. Feynman." But then Feynman said something that changed the temperature in the room. "No, I can't do this because I don't understand what this notation means. And I don't think anyone else here does either. We've just memorized the procedure." He turned to face the class. "Can anyone explain what this symbol represents? Not the definition from the book. Explain it like you'd explain it to your little sister." Silence. 20 students, all of whom could solve tensor problems in their sleep, and not one could explain what they were actually doing. The professor noticed, and he wasn't happy. But he also wasn't stupid. After class, he pulled Feynman aside and said something Feynman never forgot. "You're either going to fail or change physics. There's no middle ground with your approach." The professors were right to worry, because Feynman's approach was about to produce results that shouldn't have been possible. Senior year, the Putnam exam. If you don't know this test, imagine the hardest math problems you've ever seen. Multiply the difficulty by 10, and then give students 3 hours to solve them. The median score is usually 0 or 1 out of 100 points. Getting 20 points makes you a campus legend. Feynman scored a perfect 100 and finished in 90 minutes. His classmates were devastated. Not because he beat them, they expected that, but because of what he did after finishing. He walked around the exam room, looked at what other students were working on, and started explaining where they'd gone wrong during the exam. The proctors had to stop him, because technically it was against the rules, but the damage was done. Students who'd spent the entire semester memorizing techniques realized those techniques were useless if you didn't understand the underlying structure. And Feynman understood structure better than anyone they'd ever met. But here's what's strange. Feynman didn't think he was doing anything special. Years later, in an interview, he'd say, "I just refuse to fool myself. That's all. Most people learn to pretend they understand things. I never learned that skill. This wasn't about being smart. This was about being honest, brutally, almost painfully honest, about what you actually understand versus what you've memorized. And that honesty? It's the one thing most learners refuse to have. The pattern repeated at Los Alamos during the Manhattan Project. Feynman arrived knowing almost nothing about the specific nuclear physics required for bomb design. The other physicists, Oppenheimer, Bethe, Fermi, were already experts. Feynman was assigned to a computational group, basically doing grunt work. Within 3 months, he was leading theoretical discussions with Bohr. Within 6 months, Oppenheimer was assigning him problems that senior physicists had been stuck on for weeks. The transformation happened so fast, it made people suspicious. Was Feynman hiding previous knowledge? Was he a savant? Neither. He'd simply done the thing he always did, refused to pretend. When he didn't understand something in a meeting, he'd interrupt. Wait, what do you mean by that? Senior scientists would sometimes bristle. Didn't this kid know basic nuclear physics? But Feynman didn't care about looking smart. He cared about actually understanding. And his questions, the ones that seemed naive at first, often revealed that nobody in the room fully understood what they were talking about. They'd just gotten comfortable with the jargon. Hans Bethe, who became Feynman's mentor at Los Alamos, later said, "I learned more physics from explaining things to Feynman than I learned from any textbook, because he'd ask why about things I'd stopped asking why about decades ago." Here's where it gets uncomfortable. Because Feynman's method exposes something most people spend their entire education hiding: the difference between performing knowledge and possessing knowledge. You've felt this. That moment in a meeting when someone asks you to explain something you thought you knew, and suddenly your mind goes blank. Or that exam where you'd memorized every formula but couldn't solve a problem that was slightly different from the practice problems. Or that course you took where you got an A, and 2 months later, you couldn't remember a single concept. This isn't because you're stupid. This is because you were taught by people who didn't know how learning actually works. They taught you to optimize for grades, for certificates, for the appearance of knowledge. And appearance is easy to fake. Understanding is not. Feynman would have diagnosed you in 30 seconds. He'd have asked you to explain something you claim to know, and within 2 minutes, you'd hit a wall. A concept you can't define. A principle you can't derive, a connection you assumed but can't justify. And right there, at that wall, is where learning actually begins. But most people never stay at the wall long enough. They see confusion as failure, as evidence they're not smart enough, so they paper over it with memorization and move on. Feynman saw confusion as an invitation, as a sign that something interesting was hiding there. He'd later codify this into what teachers now call the Feynman technique, though he never called it that. The method is simple. Take something you think you understand and try to explain it to a child. Not a college student, not even a high school student, a child. And when you hit something you can't explain simply, and you will hit it, that's your gap. That's where you don't actually understand. So, you back up, rebuild your foundation, and try again. But here's the thing nobody talks about. This method is uncomfortable. It's slow. It makes you feel stupid, at least at first. Which is why most people don't do it. They'd rather feel smart while learning nothing than feel confused while learning everything. The education system makes this worse, because everything about how we structure learning is designed to hide confusion, not expose it. Lectures present clean narratives that skip over the messy parts. Textbooks show finished solutions without the 20 failed attempts. Exams test recall, not understanding. So students learn to play the game, memorize, regurgitate, forget, repeat. And then they wonder why nothing sticks, why they can pass tests but can't apply anything, why they feel like frauds in their own careers. Feynman watched this pattern for decades, and it broke his heart. He'd be invited to review textbooks for California schools, and he'd find books that were hundreds of pages of definitions with zero understanding. He'd visit physics departments and find graduate students who could derive quantum field equations but couldn't explain what a field was. He'd talk to CEOs who'd paid fortunes for executive education but couldn't explain the core concepts of their own businesses. In 1974, giving a commencement address at Caltech, he told graduating students, "The first principle is that you must not fool yourself, and you are the easiest person to fool." He was talking about scientific integrity, but he was also talking about learning. Because every time you pretend to understand something you don't, every time you highlight a passage without thinking about it, every time you memorize a formula without deriving it, you're fooling yourself. And that self-deception compounds. It becomes a habit. Until one day you realize you've spent years learning things you don't actually know. This isn't just about exams. This is about your career, your confidence. The quiet voice that wonders if you're actually competent or just good at pretending. Because here's the uncomfortable truth. Most professionals are faking it, not because they're lazy or stupid, but because they were taught to fake it. They learned to speak the language of their field without understanding the grammar. They learned to recognize patterns without understanding the principles. And as long as nobody asks them to explain from first principles, they get away with it. Until they don't. Until they're in a meeting and someone asks a basic question they can't answer. Until they're managing a team and realize they don't actually understand the work they're managing. Until they're stuck in their career because they never built real foundations, just memorized enough to pass the last test. Feynman's gift wasn't his intelligence. Plenty of people at MIT were as smart as him. His gift was permission to feel confused, to ask stupid questions, to admit ignorance, to rebuild understanding from scratch even when it takes 8 hours for one equation. Most people never give themselves that permission. They think confusion is failure. Feynman knew confusion was the only honest starting point. He'd say in later interviews, "I don't know what's the matter with people. They don't learn by understanding. They learn by some other way, by rote or something. Their knowledge is so fragile." He wasn't being arrogant. He was genuinely confused by why people chose the hard path. Memorization, cramming, surface-level learning that evaporates in weeks when the easier path was right there. Build understanding once, deeply, and it becomes intuition. You can't forget intuition. You can't lose it under pressure. It becomes part of how you see the world. But that path requires something most people aren't willing to give: temporary humility. You have to be willing to feel stupid for a few hours, to rebuild concepts you thought you already knew, to question assumptions everyone else has accepted. And in a world that rewards confidence over competence, that temporary humility feels like weakness. It's not weakness, it's the only path to actual strength. Late in his life, Feynman received a letter from a young physics student who was struggling. The student wrote, "Everyone else seems to get this easily. I have to work so hard just to keep up. Maybe I'm not cut out for physics." Feynman's response: "Study hard what interests you the most, in the most undisciplined, irreverent, and original manner possible." Translation: stop trying to learn like everyone else. Stop optimizing for grades or approval. Stop pretending to understand what you don't. Learn for real, even if it's messy and slow and makes you look foolish. Because here's what Feynman understood that most people miss. Struggle isn't learning. Struggle is a signal, a flashing warning light that says you're taking the wrong approach. Real learning, the kind that builds intuition and lasts forever, doesn't feel like struggle. It feels like clarity arriving in waves, like pieces clicking into place, like suddenly seeing a pattern you couldn't see before. When Feynman worked on a problem he truly understood, it didn't feel like work. It felt like play, like exploring, like discovering something that was always there but hidden. The struggle came before that. During the foundation building, the question asking, the confusion embracing. But once the foundation was there, the actual learning felt almost effortless. That's the metric most people miss. If learning consistently feels like punishment, like grinding through content you don't understand to get a grade you don't care about, you're doing it wrong. Not morally wrong, strategically wrong. You're choosing the path that works least well, that produces knowledge that evaporates fastest, that builds confidence on sand instead of stone. Feynman proved you can learn faster, better, and with more enjoyment by doing the one thing most education systems punish: being honest about what you don't know. But Feynman's learning method was only half of his secret. The other half, the one he rarely talked about, and that changed everything about how he approached physics, had to do with how he chose what to learn in the first place. Because while everyone else was racing to study the trending topics and impress the famous professors, Feynman was following a completely different compass. And that compass led him to questions nobody else thought were worth asking, questions that later revolutionized entire fields. But to understand that choice, we need to look at what happened the summer after Los Alamos, when Feynman almost quit physics entirely.
You drop a cup, it shatters on the floor, and then you wait. You wait for the pieces to jump back together, fly up into your hand, and become a cup again. You're going to be waiting a long time. This is so obvious that it sounds stupid to even say it. Of course broken cups don't reassemble themselves. Of course spilled milk doesn't flow back into the glass. But here's the thing that should bother you. Why not? No, seriously, why not? Because if you look at the laws of physics, all of them, the laws of gravity, electricity, magnetism, nuclear forces, every single one of them works perfectly well in reverse. Run the movie backwards and the physics still makes sense. A planet orbiting the sun? Film it, reverse it, and it's still a valid orbit. The physics doesn't care which direction time goes. Every collision of atoms, every interaction of particles, it all works forwards and backwards equally well. So if all the fundamental laws are reversible, why is the world so obviously not? We remember the past. We don't remember the future. Think about that. We have memories of yesterday, last year, our childhood. But the future? Nothing. Blank. We can guess, we can predict, we can hope, but we don't remember it. We feel like we can affect the future. We make choices, we take actions, we try to change what's going to happen. But the past? It's done. Fixed. You can regret it, you can feel remorse about it, but you can't change it. This difference between past and future is so built into our experience that we barely notice it. But it's strange. It's really strange, because the atoms don't know the difference. And now, you might think there must be some law somewhere in physics that says time only goes forward, some rule that says particles can only move this way, not that way, some fundamental principle that makes the past different from the future. But we haven't found it. After centuries of looking, we haven't found any law that distinguishes past from future. The equations work both ways. So where does the arrow of time come from? Let me show you something. Take a box. Divide it in half with a partition. Put white gas molecules on one side, black gas molecules on the other. Now remove the partition. What happens? The gases mix, obviously. The white molecules drift into the black side, the black molecules drift into the white side. And pretty soon, you have a uniform gray mixture everywhere. Now, if you wait long enough, will the gases ever unmix? Will all the white molecules ever spontaneously go back to one side, and all the black molecules go back to the other? Technically, yes. It's possible. The laws of physics allow it. If every single molecule happened to be moving in exactly the right direction, at exactly the right speed, they could all end up separated again. But the chances of this happening are so small, so incredibly tiny, that you would have to wait longer than the age of the universe. Much, much longer. The number of years you'd have to wait has more digits than there are atoms in the observable universe. So it's not going to happen. Or push a heavy block across the floor. It slides, slows down, and stops. The friction between the block and the floor brings it to rest. Now wait. Wait for the block to suddenly start moving again. Wait for the floor to push it back toward your hand. You're going to be waiting forever. The energy of the moving block didn't disappear. Energy never disappears. It transformed. It became heat. The friction warmed up the floor, just a tiny bit. The organized motion of the block, all those atoms moving together in the same direction, became disorganized motion. Atoms in the floor jiggling randomly in all directions. That's entropy. Right there, in a sliding block. The organized motion became disorganized motion. The energy spread out. The information about which direction things were moving got lost in the chaos of random thermal jiggling. Every time you see friction, every time something slows down and stops, you're watching entropy increase. You're watching organized motion become disorganized heat. You're watching the arrow of time in action. Your car brakes. Entropy increases. A ball bouncing lower and lower until it stops. Entropy increases. A pendulum slowly coming to rest. Entropy increases. It's everywhere. It's constant. It's relentless. But why? Why doesn't the block ever slide back? Why don't the gases unmix? Each individual molecule is just bouncing around randomly. There's nothing stopping any particular molecule from going left or right. So why don't they ever all go to one side? It's about counting. It's about the number of ways things can be arranged. Think of it this way. You shuffle a deck of cards. What are the chances that after shuffling, all the hearts are together, all the diamonds are together, all the clubs are together, and all the spades are together? Almost zero. Not because any particular arrangement is forbidden. Any specific arrangement of 52 cards is equally unlikely. But there's only one way to have them perfectly sorted, and there are billions and billions of ways to have them mixed up. So, when you shuffle, you almost certainly go from order to disorder. Not because of any fundamental law, but because there are so many more ways to be disordered than to be ordered. And that's entropy. Entropy is, you can think of it as a measure of disorder. But more precisely, it's a measure of how many different microscopic arrangements could produce the same macroscopic appearance. When the gas is separated, white on one side, black on the other, there's only a limited number of ways the molecules can be arranged while still looking separated. But when it's all mixed together, there are astronomically more arrangements that all look the same, gray everywhere. So the gas mixes not because mixing is a law of physics, but because there are vastly more mixed states than unmixed states. It's just probability. Overwhelming, crushing, inevitable probability. Now watch this. The laws of physics don't have a direction, but probability does. Probability says you almost always go from less likely states to more likely states, from fewer arrangements to more arrangements, from order to disorder. And that's where the arrow of time comes from. The past is when there was more order. The future is when there will be less order. We remember the past because our brains record information, and recording information requires order. We can't remember the future because it hasn't been ordered yet. Let me put it another way. Every time you break an egg, you're increasing the entropy of the universe. The egg had order, shell intact, yolk in place, everything arranged just so. The broken egg has less order, pieces scattered, yolk spreading, chaos. Could the egg unbreak? Could all those pieces fly back together and reform a perfect egg? In principle, yes. Every atom could reverse its motion. But the chances are so impossibly small that it will never happen in the lifetime of the universe. So the egg stays broken, and time moves forward. This is profound. Really think about this. The difference between past and future, this thing that feels so fundamental to our existence, it doesn't come from the laws of physics at all. It comes from statistics. It comes from counting. It comes from the simple fact that there are more ways to be messy than to be neat. Every moment of your life, you're riding the wave of increasing entropy. Every breath you take, every thought you think, every action you perform, it all increases the disorder of the universe just a little bit. And that's why time has a direction. But wait, there's a problem. If entropy always increases, if everything always moves toward disorder, then why is there any order at all? Why isn't the universe just a uniform gray soup of randomly scattered particles? Look around you. There are stars, galaxies, planets. There's life. There's you, sitting there with your incredibly organized brain, full of neurons firing in precise patterns. How did all this order come to exist in a universe that's supposed to be falling apart? The answer takes us back to the very beginning, the Big Bang. For some reason, and honestly we don't fully understand why, the universe started in a state of incredibly low entropy, extremely high order. Everything was packed together, organized in a very specific way. And ever since then, entropy has been increasing. The universe has been unwinding, moving from that initial order toward eventual disorder. So when you see a star burning in the sky, you're not seeing order being created from nothing. You're seeing the slow release of the order that was built into the universe from the beginning. The star is spending the cosmic inheritance, you might say. Think about it this way. Imagine you have a giant spring, wound up incredibly tight. That's the early universe, full of potential, full of stored order. And everything that has happened since, every galaxy forming, every star igniting, every planet cooling, every life form evolving, it's all just the spring unwinding. We're living off the low entropy of the past. Now you might ask, if the laws of physics are reversible, couldn't we argue that the future also has low entropy? Couldn't we say that the universe will eventually wind back up again? No, and here's why. Suppose you're looking at a box of gas that's half mixed, Some white molecules, some black molecules, kind of swirled together but not completely uniform. Now I ask you, what was this gas doing a few minutes ago? And what will it be doing a few minutes from now? If you assume the mixing happened by accident, by random fluctuation, then the most likely answer is that it was more mixed before and it will be more mixed after. The current partial separation is just a temporary fluctuation, and the gas is on its way back to being fully mixed. But that's not what we observe. We observe that the past had more order and the future has less. The gas was separated before, and it will be fully mixed after. This tells us something crucial. The order we see in the world is not due to random fluctuations. It's not an accident. It's a memory of an initial state of very high order. Suppose you look at one corner of a room and you see some order. Maybe the gas molecules there happen to be arranged in an unusual pattern. If this order came from a random fluctuation, then you would expect the rest of the room to be completely disordered. The fluctuation would be local. But when astronomers point their telescopes at new parts of the sky, parts they've never looked at before, they find order there too. Stars burning, galaxies spinning, the same patterns everywhere. This tells us the order is not a fluctuation. The order is universal. It came from the beginning. So the entire arrow of time, the entire distinction between past and future, traces back to one fact. The universe started with low entropy. Everything else follows from that. Why do we remember the past but not the future? Because memories are records, and records require order. The low entropy of the past allows records to be formed. The high entropy of the future doesn't. The whole structure of our experience, cause and effect, memory and anticipation, birth and death, it all traces back to entropy. The Big Bang wasn't just an explosion. It was an explosion of order, a release of potential. And everything that has happened since, every star, every planet, every life form, every thought you've ever had, is riding that wave of increasing entropy. We don't know why the universe started that way. We don't know what set up those initial conditions. It remains one of the great mysteries. But we do know this: the arrow of time points from low entropy to high entropy, from order to disorder, from the past to the future, and there's no escaping it. Now, people sometimes get confused. They look around and they see order. They see crystals forming. They see plants growing. They see babies being born and developing into complex adults. And they ask, doesn't life violate entropy? Aren't living things becoming more ordered over time, not less? No, life doesn't violate entropy, not even close. Yes, a growing plant becomes more ordered. Yes, a developing embryo becomes more complex. Yes, your brain is an incredibly organized structure. But none of this happens for free. To grow, a plant absorbs sunlight. That sunlight is low entropy energy, organized, concentrated, coming from one direction. The plant uses that energy to build its structures, and in the process, it radiates heat back into the environment. That heat is high entropy energy, disorganized, spread out, going in all directions. The total entropy, plant plus environment, increases, always. You are the same way. You eat food. Food is organized, complex molecules arranged in specific patterns. Your body breaks down that food, extracts the useful energy, builds and repairs your tissues, and in the process, you radiate heat. You exhale carbon dioxide. You produce waste. The order in your body is borrowed. It comes from the order in your food, which came from the order in sunlight, which came from the order in the sun, which came from the order in the gas cloud that formed the sun, which came from the Big Bang. So you are not fighting entropy, you are surfing it. Life is not a violation of the second law of thermodynamics. Life is a particularly interesting way of increasing entropy. We are entropy increasing machines that happen to be conscious. Think about that for a moment. Every breath you take increases the entropy of the universe. Every thought you think, because thinking requires energy, and energy use produces heat, increases the entropy of the universe. Every moment you're alive, you're contributing to the great unwinding. But along the way, along this process of increasing entropy, you get to experience things, you get to think, you get to wonder, you get to love and create and discover. Life is what entropy looks like when it gets complicated. And the order that makes you possible, the low entropy that allows your existence, it's not just from yesterday's breakfast. It traces back through an unbroken chain, back through the food chain, back through the ecosystem, back through the formation of the earth, back through the ignition of the sun, back through the collapse of gas clouds, back through the formation of the first stars, back, all the way back to whatever happened at the beginning. You are connected to the origin of the universe, not metaphorically, physically. The arrow of time that runs through you is the same arrow that runs through everything. The entropy that governs your life is the same entropy that governs the stars. When we study physics, we study the fundamental laws, the equations that govern particles and forces and fields. And these laws are beautiful, they're elegant, they're reversible, but they don't tell the whole story. The laws tell you what can happen. They don't tell you what does happen. For that, you need initial conditions. You need to know where things started. And the arrow of time, the distinction between past and future, comes from those initial conditions, not from the laws themselves. This is a profound distinction. The laws are eternal and symmetric. The world is temporal and asymmetric. The difference comes from history, not from physics. We often think of physics as telling us what the world is. But really, physics tells us what the world can be. The world itself, with all its complexity and history and direction, is one particular realization of those possibilities, one particular path through the space of what's allowed. Why this path? Why these initial conditions? Why this arrow of time? We don't know. Maybe we'll figure it out someday. Maybe we won't. But the question itself, the question of why the universe is the way it is, rather than some other way, that question is part of what makes physics so fascinating. We're not just cataloging facts. We're trying to understand why reality is real, why things happen, why time flows, why we're here at all. Now, some people find this depressing. The universe is winding down. Everything falls apart eventually. Every structure, no matter how beautiful or complex, will ultimately dissolve into chaos. But I don't see it that way. Think about what it means to be alive right now. You exist in this narrow window, this brief era between the ordered past and the disordered future, when complexity is possible, when stars can burn, when planets can form, when molecules can arrange themselves into living things. You are not separate from this process. You are this process. You are entropy increasing in a particularly interesting way. So when I say we're all going to the same place, I mean it literally. Every structure dissolves. Every order becomes disorder. Every complex thing eventually falls apart. Stars burn out. Planets cool. Life ends. Civilizations crumble. Eventually, given enough time, the universe reaches maximum entropy, heat death, equilibrium. Nothing more happening ever again. But don't let that make you sad. The fact that entropy increases, the fact that time moves forward, the fact that everything eventually ends, this is not a flaw in the universe. This is what makes the universe interesting. Without increasing entropy, nothing would happen. There would be no change, no flow, no story, just static equilibrium, forever. The arrow of time is what gives us moments. The march toward disorder is what gives us events. The slow unwinding of the cosmic spring is what gives us everything. You exist because entropy increases. You experience time because entropy increases. You can make choices and have effects because entropy increases. So, Yes, we're all going to the same place. But the journey is everything. And right now, you're on it. You are made of atoms that were forged in ancient stars. You are organized by patterns that trace back to the beginning of time. You are conscious in a universe that is mostly not. And for this brief flicker, this tiny window between the ordered past and the disordered future, you get to be here. The universe is winding down. But right now, in this moment, it's still wound up enough for you to exist, for you to think, for you to ask questions about why anything is the way it is. That's not tragedy. That's something, isn't it? The arrow only points one way, and that's what makes every moment matter.
Let me tell you something that's going to make you uncomfortable. The difference between the rich and everyone else isn't what you think it is. It's not intelligence. It's not education. It's not even luck or connections or family money. Apause, I've spent years studying successful people. Not just the wealthy, but the truly successful. The people who built something meaningful, who created lasting value, who went from nothing to extraordinary. And I found one single habit that shows up in every single one of them, including Richard Feynman, who wasn't trying to get rich but ended up incredibly successful anyway. This habit isn't sexy. It's not what motivational speakers talk about. It's not what business books teach. It's so simple that when I tell you what it is, you're going to think I'm wasting your time. But this habit is the difference, the real difference, between people who accumulate wealth and success and people who work just as hard but stay broke, between people who create value and people who just exchange time for money. Direct address? And here's what's going to shock you. Most people actively avoid this habit. They think it's a waste of time. They think it's inefficient. They think successful people must be doing something else, something more complicated. They're wrong. Today, I'm going to show you this habit. I'm going to prove why it works. And I'm going to show you exactly how to implement it starting today. Because once you understand this habit, once you really get why it separates the rich from everyone else, you can't unsee it. You'll start noticing who has it and who doesn't. And you'll understand why some people keep winning while others keep struggling. So I walk across stage, or let me start with a story, because this story reveals everything. It's the 1940s. Feynman is at Los Alamos working on the Manhattan Project, the atomic bomb, and they're paying him, not a fortune, but decent money, more than he's ever made before. And you know what he does with his free time? When he's not working on the bomb, when he could be relaxing, playing, doing anything, he studies, he thinks. He works on physics problems that have nothing to do with his job, problems nobody's paying him to solve, problems that seem completely pointless. His colleagues think he's crazy. Feynman, you're already working all day on the most important project in the world. Why are you spending your free time on random physics problems? And Feynman says something interesting. He says, I'm not working, I'm playing. I'm figuring things out. I'm building my understanding. So let that land as though I fast forward 20 years. Those pointless problems he worked on, they led to quantum electrodynamics, Nobel Prize, revolutionary discoveries, consulting opportunities, speaking fees, book deals. The work he did for free, for fun, for no reason other than curiosity. That work made him far more successful and wealthy than his actual paid job ever could. I'll just make the connection, and that's the habit. That's the difference. That's what separates the rich from everyone else. Their direct statement: the rich invest in assets that compound. The poor trade time for money. Now, before you roll your eyes and think, I've heard this before. Let me show you what this really means. Because most people completely misunderstand this concept. Faktra explained carefully. When most people hear invest in assets, they think about money, stocks, business investments. But that's not what I'm talking about. That's not what separated Feynman from everyone else. That's not what separates the truly wealthy from the merely high income. The habit is this: investing your time in building knowledge, skills, and understanding that compound over time. Most people trade their time for money. They work, they get paid, they stop working. The money stops. Linear relationship. 40 hours of work equals 1 paycheck. Stop working those 40 hours, you don't get the paycheck. But the rich, they invest time in building something that pays them repeatedly. knowledge that solves multiple problems, skills that create multiple opportunities, understanding that generates multiple insights. A. Make it concrete. T. Feynman invested time in deeply understanding physics. Not just learning equations, not just memorizing facts, deeply understanding how the universe works. And that understanding, it paid him over and over. Every problem he solved used that understanding. Every lecture he gave drew from that understanding. Every book he wrote leveraged that understanding. Every consulting opportunity came from that understanding. Rate point one investment of time, multiple returns. That's compound interest. That's how you get rich. But most people don't do this. Let me show you what most people do instead. Tell this story. I was talking to someone recently. Smart person, hardworking, complaining about being broke. I ask, what did you do last weekend? Watched Netflix, played video games, scrolled social media. What about the weekend before? Same. And what are you doing this weekend? Probably the same. A pause. Or no. I'm not judging leisure time. I'm not saying you can't relax. But here's the question. What are you building? Every weekend, every evening, every bit of free time. Are you building something that compounds? Or are you just consuming and forgetting? Make the contrast. The rich use their time to build assets, knowledge, skills, networks, understanding, systems, content, intellectual property. The poor use their time to consume, entertainment, distraction, information they'll forget, experiences that don't compound. Refresh you jet directees, and the gap between these two approaches gets bigger every single year because the person building assets, their returns compound. They get exponentially better. Their knowledge builds on itself. Their skills reinforce each other. Their network grows through referrals. The person consuming, they're in the same place. Same skills, same knowledge, same capabilities. They might have new memories from Netflix shows, but nothing that creates value. Falls or posy, that's why the rich get richer. Not because they're greedy. Not because the system is rigged. But because they're investing in compounding assets while everyone else is renting their time. Tell another Feynman story. Let me show you what this looks like in practice. Concrete example. Feynman is teaching at Caltech. They're paying him a salary to teach. And he takes that job seriously. He prepares lectures. He meets with students. He does his job. But he also does something else. He invests enormous time in understanding how to teach, how to explain, how to make complex ideas simple. Just build this, he doesn't have to do this. Nobody's paying him extra to be the best teacher. He could do adequate lectures and still get his paycheck. But he invests the time. He thinks deeply about education. He experiments with different approaches. He refines his explanations. He makes teaching itself a subject of study, a share the payoff at, and what happens? Those lectures become legendary. Students record them. They get published as the Feynman Lectures on Physics. They sell millions of copies. They're still selling today, decades after his death. His investment in understanding teaching, something nobody paid him extra to do, created an asset that pays indefinitely. Book royalties, licensing fees, reputation that led to speaking opportunities. Hakem make the point, one investment in learning how to teach well. Infinite returns. That's the habit. That's the difference. Address the objection. Now, some of you are thinking, that's great for Feynman. He was a genius physicist. I'm not. How does this apply to me? Let me show you. Let me give you examples from people who aren't Nobel Prize winners. Share modern examples. There's a plumber I know, been plumbing for 20 years, makes decent money, not rich but comfortable. Most plumbers at his level. They come home, they're tired, they watch TV, they relax. Nothing wrong with that. But this guy, he spent his evenings for 2 years building a YouTube channel, teaching people basic plumbing repairs, how to fix a leaky faucet, how to unclog a drain, how to replace a toilet. Continue the story. Was anyone paying him to make those videos? No. Did it take time away from relaxing? Yes. Did his friends think he was crazy? Absolutely. But now, that channel makes more than his plumbing business. Passive income, ad revenue, sponsorships, product recommendations, online courses. He invested time in creating an asset, his knowledge shared publicly. And now that asset pays him while he sleeps. Another example, or take this woman I met. She's an accountant, normal job, normal salary. But she noticed she kept answering the same tax questions from friends and family. So she started a blog. Every week, she'd write one post explaining a common tax question in simple terms. did this for 3 years. Nobody paid her for it, just invested her time. The doctor share the result is now. That blog gets hundreds of thousands of visitors. She's written an e-book that sells constantly. She gets consulting clients from it. She's become a recognized expert in her niche. Her salary from her accounting job hasn't changed much, but her wealth has exploded because she built an asset that compounds. Make it universal to see the pattern. It's not about being a genius. It's not about having some special talent. It's about investing time in building assets instead of just trading time for money. Get philosophical now. Here's why most people don't do this. Here's why most people stay poor even when they work hard. Because building assets feels like wasted time. It doesn't pay immediately. It doesn't show results right away. It looks like you're working for free. Free explain the psychology. Trading time for money feels good. You work 8 hours. You get paid. Immediate gratification. Clear cause and effect. You can see the value of your time. Building assets feels bad. You work for months or years with no pay. No immediate results. No clear progress. It feels like you're wasting time that could be earning money. Ace pointer. So most people choose the thing that feels good but keeps them poor. They trade time for money. Linear returns. No compounding. The rich do the thing that feels uncomfortable but makes them wealthy. They build assets. Even when it doesn't pay immediately. Even when it seems pointless. Even when everyone thinks they're crazy. Fair share personal example. Let me tell you about my own experience with this. 5 years ago, I was trading time for money. Freelancing. Working hard. Making decent income. But capped. Because there are only so many hours I could work. And I decided to start writing. Not for clients. Not for money. Just writing publicly about things I was learning. Investing time in building a body of work. Aish continues, my freelance clients thought I was stupid. Why are you spending time writing for free when you could be taking more paid work? Because I understood the habit. I understood that building an asset, even unpaid, would compound in ways that hourly work never could. I share the results of fast forward 5 years. That body of work, it's led to speaking opportunities, book deals, consulting clients who pay 10 times what my hourly rate used to be, products I've created. Systems I built. My income has increased 5 times, not because I work 5 times more hours, because I built assets that compound. K-Pause, that's the difference. That's the habit. That's what separates the rich from everyone else. Packer get practical. So how do you actually implement this? How do you start building compounding assets instead of just trading time for money? Let me give you the framework. The exact process you can use starting today. Extra present this clearly. For first, identify what you know that others want to know. Everyone knows something. Everyone has skills. Everyone has experience. What's yours? Maybe you're good at Excel. Maybe you understand social media. Maybe you know how to negotiate. Maybe you've figured out how to budget effectively. Maybe you understand gardening. Maybe you can cook well. Fart continue. Don't dismiss it as everyone knows this. They don't. What's obvious to you is mysterious to someone else. What's easy for you is hard for someone else. Find that thing, the knowledge or skill you have that others would benefit from. Second step is second. Document your knowledge publicly. This is crucial. Don't just know things, share them publicly, where people can find them, where they create value, where they compound. Write blog posts, make videos, tutorials, build courses, start a podcast, share on social media. Doesn't matter what format. What matters is that you're creating assets that exist independently of your time. Research explain why, when you document knowledge publicly, you create assets. Those blog posts, they work for you 24/7. Those videos, they reach people while you sleep. Those tutorials, they help people in different time zones. One investment of time, infinite potential returns. Third step of third, do this consistently for at least 2 years. This is where most people fail. They try for 2 months. They don't see immediate results. They quit, but assets take time to compound. Feynman didn't become famous overnight. That plumber didn't blow up in 6 months. That accountant didn't get rich in 1 year. Make this clear, consistency over time is what creates compounding. 1 blog post does nothing. 100 blog posts start to matter. 500 blog posts make you an authority. 1 video is invisible. 100 videos build an audience. 500 videos create a business. All right, fourth step of fourth, reinvest your returns. As your assets start paying off, and they will, don't just spend that money. Use it to build more assets. Use the time freedom to learn more. Use the money to hire help so you can create more. This is how compounding accelerates. The returns from your assets help you build more assets, which generate more returns, which let you build more assets. Make it concrete. That plumber. His YouTube income let him hire someone to help with his plumbing business, which freed up his time to make more videos, which grew his channel faster, which generated more income, compounding on top of compounding. Ace pause, bring it together. So that's the framework. Identify what you know. Document it publicly. Do it consistently for 2 years. Reinvest your returns. 4 steps. Simple. Not easy, but simple. Address the resistances now. I know what you're thinking. I know the objections that are coming up. I don't have time. I'm already working full time. I have a family. I have obligations. Respond to this if Feynman had obligations too. He was working on the atomic bomb. He had a dying wife. He had responsibilities. But he found time, not by working more hours, by choosing differently about his free time, by investing instead of consuming. You already make it practically. You don't need 8 hours a day. You need 1 hour, 3 times a week. That's it. 3 hours a week invested in building assets instead of consuming content. 3 hours a week for 2 years. That's about 300 hours total. That's enough to create something significant, a course, a substantial body of written work, a serious YouTube channel, a valuable skill set. Compare that to 300 hours of Netflix. Which one compounds? Which one makes you richer? Bahay another objections. But what if I fail? What if I spend all this time and nothing happens? Let me tell you about Feynman's approach to this. Ours share this story. Feynman worked on problems for years that went nowhere. He explored ideas that didn't pan out. He invested time in approaches that failed. But he never considered that time wasted. Why? Because even when specific projects failed, the understanding he built always compounded. Facts explain. When you invest time in learning, in building skills, in creating, even if that specific project doesn't succeed, you're not back at zero. You're ahead. You know more. You can do more. You understand more. That knowledge transfers. Those skills apply elsewhere. That understanding opens new doors. Make the point. The only true failure is not investing at all, not building anything, just consuming and trading time for money your entire life, because then years pass and you're in the same place. Same skills, same knowledge, same earning potential. Actually, often less because your skills become obsolete and you never updated them. Para share a powerful insight P. Here's what I've learned studying the wealthy. They all have this abundance mindset about time investment. They don't ask, will this specific thing pay off? They ask, will this make me more capable? Will this build skills that compound? If yes, they invest the time, even if the immediate payoff is unclear, because they trust that capability compounds into opportunities they can't even imagine yet. To tell this story, Feynman spent time learning to draw. Nobody paid him. It wasn't related to physics. His colleagues thought it was a waste, but that investment, it taught him to see things differently, to observe more carefully, to understand visual representation, all of which made him better at physics. Plus, it led to friendships with artists, which exposed him to different ways of thinking, which influenced his approach to problems, which made him more creative in his physics work. Point is one investment, multiple unexpected returns. That's how compounding works. You can't predict all the ways that knowledge and skills will pay off, but you can trust that they will. And Chuck Jet emotional, let me tell you what really breaks my heart. I see people, smart people, capable people, hardworking people who spend 30 years trading time for money, working hard, making decent incomes, but building nothing that compounds. And then they hit 50, 60, and they realize they can't retire. They can't stop working, because if they stop trading time for money, the money stops. They have no assets, nothing that pays them without their active labor. Pause. That's the trap. That's what happens when you don't invest in compounding assets. You work hard your entire life, and you're still dependent on your next paycheck. Contrast, but the people who invested time in building assets, their 50s and 60s look completely different. They have books that still sell, courses that still run, investments that still pay, systems that still work, knowledge that still creates opportunities, networks that still generate referrals. They have freedom, real freedom, not just money, but time freedom, because their assets work for them. thus make the connection. That's what Feynman had. Even late in life, dying of cancer, his assets were still working. His books were selling. His lectures were being studied. His understanding was creating value. He invested in assets that outlived him. That's the ultimate compound return. Get practical again. So let me give you specific actions. Things you can do this week to start building compounding assets. I present these action 1. Identify one skill you want to build. Something valuable. Something others would pay for or benefit from. Commit to investing 3 hours a week for the next year building that skill. Action 2. Start documenting what you're learning. Blog posts, videos, social media posts, doesn't matter where. Just start creating public artifacts of your knowledge. Action 3. Connect with one person who's further along than you. Learn from them. Build that relationship. Networks compound too. Continue action 4. Cut 3 hours of consumption from your week. 3 hours of TV, social media, gaming, whatever. Replace it with building assets. That's where your investment time comes from. Action 5. Set a 2-year deadline. Commit to doing this for 2 years before judging results. Because that's how long compounding takes to become visible. Pause 5 actions. Start this week, not next month, not when you have more time. This week. So for tell final stories, let me end with one more Feynman story. This one shows the power of compounding over a lifetime. Feynman dies in 1988. He's gone. But his assets keep working. His books keep selling. Millions of copies. Translated into dozens of languages. Students around the world learn from them. His lectures keep teaching. They're online. Free. Millions of views. Inspiring new generations of physicists. Build this his ideas keep spreading. His approach to thinking, his method of understanding, his way of questioning, they influence fields beyond physics, computer science, biology, education, business. His estate keeps earning. Royalties, licensing. His family benefits from work he did decades ago. Glossars make the final point, that's the ultimate compound return. Assets that outlive you, work that matters beyond your lifetime, value that perpetuates. And it all started with a simple habit, investing time in building knowledge and sharing it instead of just trading time for money. Also walk to center stage. So here's what I want you to understand, really understand. The difference between the rich and everyone else isn't complicated. It's not mysterious, it's not unfair, it's a habit, a choice. A way of thinking about time, a direct statement. Do you trade your time for money? Or do you invest your time in assets that compound? That single habit, repeated over years, creates all the difference between wealth and poverty, between freedom and dependence, between building something lasting and just getting by. This is positive. You have the same hours as everyone else, the same 24 hours a day, the same 7 days a week. The question is, what are you building with those hours? Final challenge. So here's my challenge to you. Look at your week. Look at where your time goes. How much are you trading for money? How much are you consuming for entertainment? How much are you investing in compounding assets? Be honest, really honest. Pause and then make a change. Take 3 hours, just 3 hours, and invest them in building something that compounds. Do that every week for 2 years. And then tell me if this habit doesn't separate you from where you are now. Tell me if you're not richer, not just in money, but in capability, in opportunity, in freedom. Final thought, Feynman wasn't trying to get rich. He was trying to understand. But understanding is an asset that compounds into everything, including wealth. That's the lesson. That's the habit. That's the difference. Smiley, start building your assets today. Your future wealthy self will thank you. Thank you. A 5 beat teach. And if you want more insights into how successful people actually think and work, if you want to understand the real habits that separate the achievers from the dreamers, do me a favor, like this video and subscribe to the Mind of Richard Feynman channel. We're uncovering the real principles behind extraordinary success, not motivational fluff, actual practical habits you can implement. Join us, let's build assets together. See you in the next one.
Many people believe that focus is simply forcing yourself to stare at something for hours. But that's as ineffective as trying to push a wall with your bare hands. Here's the secret. Energy must be channeled, not wasted. Just like light, when concentrated into a laser beam, gains the power to cut through steel, your attention, when directed with relentless precision, has the power to break through any barrier in life. Pay close attention to me, because this can change the way you see yourself. Your brain works like a particle accelerator. Billions of electrical signals are firing every second, colliding, crashing, creating new connections. But without direction, all of that activity is chaotic, scattered, without results. When you learn to create focus tracks, the same way physicists guide beams of particles in straight lines with magnetic fields, what was once confusion turns into organized power. This is the first secret to training your brain like a genius. It's not about thinking of everything. It's about thinking of one thing with such intensity that the world around you disappears. And here is where discipline comes in. Don't confuse discipline with suffering. Discipline is, in fact, the art of simplification. If you can't explain something in a simple way, it means you haven't understood it. The same applies to your life. If what you're doing feels too complicated, it's because you haven't yet found the clarity that generates true focus. So here's the first exercise I want you to do. Choose one goal, just one, and write it down in a single sentence. Simple, clear, and direct. If you can't summarize it, then you don't yet understand what you truly want. Now, take a deep breath and reflect. How many years have you lost trying to embrace everything, when in reality the secret was to reduce? Think of Newton. Think of Einstein. Geniuses who dedicated decades to just a handful of questions, and because of that, they achieved greatness. Your focus is your most powerful weapon. Use it like a laser beam. Your brain is like a telescope. If you point it at nothing, you'll see only darkness, but if you adjust the lens and choose a single star, suddenly the entire universe begins to reveal itself. Focus is exactly that, the ability to eliminate the noise so you can see what truly matters. But here's the real question. How do you develop greater focus? Pay attention, because here's the truth almost no one dares to say. Focus is not something you find. It's something you train, exactly like a muscle. No one is born with unshakable discipline, but anyone can build it. Think of the physicist who spends hours adjusting an experiment. Every tiny adjustment is a victory against distraction. The same applies to you. Want more focus? Create environments where distraction has no place. Remove the excess. Eliminate notifications. Write down exactly what you'll do in the next hour and do only that. Does it sound simple? It is simple, but that's precisely why it works. If you can't create an environment that favors focus, then you don't yet understand your own mind. Training focus is training your mind to choose, and every choice is an act of power. Don't fool yourself. Every time you give in to distraction, you're strengthening the muscle of weakness. Every time you say no to an interruption, you're strengthening the muscle of focus. And here's a practical exercise for you. Every single day, set aside 30 minutes to concentrate on just one task without interruptions. If your mind starts to wander, bring it back, no matter how many times it happens. This is exactly like training physical endurance. At first, it hurts, but then you realize that pain transforms into strength. In just a few weeks, you'll have developed the ability to dive deeply into anything you choose. Remember this: the brain is plastic. It molds itself according to how you use it. If you feed it distraction, it becomes scattered. If you feed it focus, it sharpens like a blade. The choice is in your hands. And now let me tell you something that might sting a little. If you quit just because someone laughed at you, it means you haven't yet understood what inner strength really is. If you stop because you feel tired, it means you still haven't realized that the body can always go further when the mind commands. Focus doesn't grow in times of comfort. It's born when you face pain, sacrifice, and still choose to keep going. That's how steel is made, through fire. Here's a powerful habit for you. Before going to sleep, write down in a notebook, what did I do today that brought me closer to my goal? What distracted me? What could I have done better? This simple act, repeated every day, creates a vigilant mind. It's like a scientist reviewing every detail of an experiment until nothing escapes. Do this for just a few weeks and you will no longer be the same person. The regret of not having lived up to your potential is infinitely heavier than the pain of discipline. The pain of waking up early, of studying when you don't feel like it, of pushing forward when nobody believes in you. That pain is temporary, but the regret of not giving your all is eternal. So make a pact with yourself now. Train your mind like a genius. become unbreakable. Now imagine this. You're facing a difficult problem, one of those that feels impossible. Most people give up because they see the challenge as torture. But a genius looks at that same problem as if it were a game. That's exactly how great minds transform physics into something fascinating. Physicists don't study out of obligation. They play with concepts. They sketch. They create funny metaphors. And that's why they're able to go so deep. And here lies one of the greatest secrets of humanity about learning. When you enjoy what you study, you don't just learn more. You also train focus and discipline to levels that seem almost superhuman. So what's the difference between someone who quits quickly and someone who dives deep into an idea until they master it? The difference lies in emotion. The one who finds joy in the process doesn't need external motivation, because the very act of studying, practicing, or creating becomes its own reward. This is the key you need to understand. Focus is not sustained by brute force, but by fascination. Want to improve your focus and discipline? Transform every task into an experiment. Ask yourself, how can I make this more interesting? How can I see this problem from a new perspective? By doing this, you activate curiosity. And curiosity is like a magnet for the mind. It pulls your attention without effort. The first rule is not to fool yourself, and you are the easiest person to fool. That means you can't trick yourself into believing you have focus if you secretly hate the process. The brain rejects what doesn't make sense to it, but when you connect emotionally with what you're doing, focus arises naturally. And every time you practice this kind of playful, creative study, your discipline grows without you even noticing, because discipline stops being a prison and becomes freedom. Discipline is not just about enduring pain. True discipline is being so deeply involved in what you do, so passionate about it, that continuing becomes the most natural path. That is how you create not only unshakable focus, but a mind that learns and expands every single day. And this, right now, could be the moment when you decide to change everything. Your mind is your greatest weapon. It's not external resources, it's not luck, it's not what others say. It's your ability to train your brain like a genius, to develop relentless focus, to build discipline even when no one else believes in you. That is what will define how far you can go. Stay with me here, because you need to understand this. The world is already full of ordinary people, distracted, trapped in empty routines. But those who decide to master their focus, those who cultivate discipline and curiosity, they become unstoppable. They don't play by the rules, they create the rules. They don't wait for opportunities, they build them. So here's the question. Will you keep being just another face in the crowd? Or will you take command of your mind and transform your life into something extraordinary? Be honest with yourself. How many times have you promised to change, only to give up at the first difficulty? How many times have you let distraction win? That ends today. Make a pact right now. Sacrifice what you must, but never sacrifice your future. Train your brain, sharpen your mind, and success will simply become an inevitable consequence. And I want you to do something right now. Write in the comments, I am unstoppable, to seal this commitment with yourself. This isn't just a phrase, it's an act of decision. Click subscribe, turn on the notification bell, and hit the like button, because this is only the beginning of a journey that can completely transform your life. This is the moment when you stop living as a spectator and start acting as the protagonist. Remember this, regret weighs forever, but discipline shapes champion. In your hands lies the power to write a new story. So stand up, take action, and prove to the world and to yourself that your focus is truly unstoppable.
We traveled back in time, excited. We thought we had done well. Look at our technology, look at our data, look at our confidence. He wasn't impressed. He was angry, not loud anger, the dangerous kind, the kind that comes from disappointment. He looked at our books, our lectures, our confident explanations, and he stopped us immediately. You don't understand, he said. You've learned to talk about it. That hurt. It was supposed to. We showed formulas. He asked simple questions, not advanced ones, basic ones. Why does it work? What does it actually mean? What would happen if it didn't? Silence. We knew the steps. We didn't know the reason. Somewhere along the way, we replaced curiosity with credentials. We replaced doubt with confidence. We replaced thinking with repetition. And worst of all, we stopped admitting when we didn't know. That's when learning died. He reminded us of something brutal. If you can't explain an idea simply, you don't understand it deeply. And if you don't understand it deeply, you have no right to be certain. Nature doesn't care how elegant your theory sounds. It doesn't care who approved it. It only cares whether it's right. Reality is cruel that way and honest. He wasn't angry because we were wrong. He was angry because we were comfortable being shallow, because we taught answers without questions, because we trained people to pass exams, not to think, because we forgot that the joy of discovery comes from confusion first. Understanding is hard, that's the point. If learning feels easy all the time, you're probably not learning. You're just memorizing. Before we left, he said one last thing. Never fool yourself, and remember, you are the easiest person to fool. That's why he was angry, and that's why we should be too. If you want, next weekend, confusion is the enemy of understanding, but not the honest kind. The real enemy is the confusion we pretend isn't there, the fog we decorate with big words and call knowledge. The moment we stop saying, I don't know, learning doesn't slow down. It stops completely. From that moment on, we're not discovering anything. We're just repeating noises that sound intelligent. People think the opposite of understanding is ignorance. That's wrong. Ignorance is clean. Ignorance knows it doesn't know. Confusion that thinks it understands is poison. It creates confidence without clarity, certainty without truth. And once that happens, curiosity dies. Why ask questions when you believe you already have the answers? Look closely at how we learn things. We memorize definitions. We memorize formulas. We memorize steps. Then we mistake recognition for comprehension. We hear familiar words and feel smart. But ask one simple question, why does this work? And suddenly the room goes quiet. That silence is not a failure of memory. It's a failure of understanding. We've trained ourselves to survive systems, not to understand reality. Exams reward recall, not insight. Presentations reward polish, not depth. The result is a generation that can recite explanations but can't reason through problems. They know the vocabulary of ideas without touching the ideas themselves. And here's the uncomfortable truth. Most of what we confidently explain, we don't actually understand. We've learned to move symbols around without knowing what they represent. We manipulate equations like rituals, hoping the answer appears at the end. When it does, we celebrate. When it doesn't, we blame the math, not our thinking. Real understanding is slow, it's frustrating, it feels stupid before it feels smart. You get lost, you contradict yourself, you ask questions that sound childish, and that's exactly how you know you're doing it right. Understanding begins the moment you're willing to sit inside confusion instead of escaping it with memorized answers. But we hate that discomfort, so we hide it. We cover confusion with authority. We say, that's just how it is, or trust the theory, or experts agree. Sometimes experts are right, sometimes they're wrong, but even when they're right, borrowed certainty is not understanding. It's obedience. Nature doesn't care what you believe. It doesn't care how confident you sound or how many people agree with you. Reality has no respect for reputation. It only responds to what is actually true. You can fool your audience, you can fool your students, you can fool yourself, but you can't fool nature. That's why pretending to understand is so dangerous. It blocks progress, it freezes curiosity. Once you believe you understand something, you stop testing it. You stop poking at it. You stop asking what would happen if one assumption were wrong. And every major breakthrough in history came from someone doing exactly that, questioning what everyone else had stopped questioning. True understanding is not about having answers. It's about knowing which questions matter. It's about being able to explain an idea in plain language, not because simplicity is fashionable, but because clarity is a test of truth. If an idea only works when wrapped in complexity, there's a good chance it doesn't work at all. And here's the part people don't like to hear. Confusion is not something to eliminate quickly. It's something to respect. Confusion is a signal. It's reality telling you that your current model is incomplete. Ignore that signal and you build castles on sand. Listen to it and you rebuild your thinking from the ground up. This is why intellectual honesty matters more than intelligence. Smart people can be confidently wrong. Honest thinkers can be temporarily confused and eventually right. Progress belongs to the second group, not the first. The discipline is brutal but simple. Never confuse familiarity with understanding. Never hide behind jargon. Never accept an explanation. You can't explain yourself. And most importantly, never be embarrassed to say, I don't know yet, because I don't know is not weakness. It's the doorway. It's the starting point of every real idea that ever changed how we see the world. Confusion isn't the enemy when you face it. It becomes the enemy only when you pretend it isn't there. We mistook memorization for knowledge, and the mistake was so convenient that we built entire systems around it. Memorization is fast, it's measurable, it looks like progress. You can test it, grade it, certify it, and move on. Real knowledge is none of those things. It's slow, uncomfortable, and difficult to standardize. So we chose the easier substitute and told ourselves it was the real thing. Memorization gives the illusion of competence. You recognize the formula, the definition, the historical date, and your brain signals success. Familiarity feels like understanding, even when it isn't. You can repeat the words, but if the situation changes slightly, if the problem is framed differently, or the assumptions shift, the knowledge collapses instantly. That collapse reveals the truth. Nothing was understood, only stored. Knowledge is not the ability to recall information on demand. Knowledge is the ability to reason when memory fails. It shows itself when you're forced to think without a script, when there's no checklist to follow and no example to copy. If removing the notes removes your understanding, you never had understanding to begin with. We train people to pass tests, not to think. We rewarded speed over depth, certainty over curiosity. The student who asked too many questions slowed the class down. The one who repeated the answer efficiently was praised. Over time, the lesson became clear. Don't explore, perform, don't wonder, deliver. This is how intelligent people become fragile thinkers. They know a lot, but only inside familiar boundaries. The moment a problem refuses to fit the template, panic sets in. They search their memory harder instead of questioning their assumptions. But memory cannot save you when the situation is new. Only understanding can. Memorization is brittle. It breaks under pressure. Knowledge bends and adapts. When you understand something, you can rebuild it from scratch. You can derive it. You can explain why it must be that way and not some other way. When you've only memorized, all you can do is hope the question looks familiar. And here's the uncomfortable part. Most systems don't care. Memorization is efficient. It scales. It produces impressive short-term results. But long-term, it creates thinkers who are afraid to be wrong. Because when your value is tied to recall, admitting uncertainty feels like failure. So people defend weak ideas instead of questioning them. Real knowledge invites doubt. It survives it. In fact, it depends on it. Understanding grows when you stress test ideas, when you push them into uncomfortable territory and see what breaks. Memorization avoids this at all costs. It preserves answers by never challenging them. There's a reason people cling to memorized explanations. They're safe. They come pre-approved. They carry authority. You don't have to take responsibility for them. If they fail, you can say, that's what I was taught. Understanding doesn't give you that escape. When you understand something, you own it. And ownership is risky. But that risk is where thinking begins. Knowledge is not something you store, it's something you can use. It shows up when you can predict outcomes, not just describe past ones. When you can spot nonsense, even when it's wrapped in impressive language. When you can simplify without losing truth. The tragedy is not that memorization exists. It has its place. The tragedy is that we stopped demanding more. We stopped asking students to explain ideas in their own words. We stopped valuing slow, careful reasoning. We stopped rewarding the struggle that precedes real insight. The cost is everywhere. People argue confidently about things they don't understand. They defend positions they can't justify. They confuse agreement with truth and repetition with evidence. All of it traces back to the same error, mistaking recall for comprehension. If you want to know whether you truly understand something, remove the script. Change the context. Ask what-if questions. Try to teach it without using the original words. If the idea survives, you've learned something real. If it collapses, don't be embarrassed. That collapse is the beginning of knowledge, not the end. Memorization feels like progress. Understanding is progress. One fills your head, the other changes how you think. Math became decoration instead of meaning the moment symbols started. Impressing us more than understanding. Equations turned into ornaments, something to display, not something to think with. Lines of symbols were treated like proof of intelligence, even when no one could explain what they actually described. The math looked right, sounded sophisticated, and that was enough. Or so we told ourselves. At its core, math is not a performance. It's a language for describing reality with precision. Every symbol stands for an idea, every operation for a relationship. When those ideas are lost, the symbols become empty. You can move them around, manipulate them, and still have no idea what you're saying. That's not mathematics, it's ritual. Somewhere along the way, we started teaching procedures without meaning. Do this step, then that step, and you'll get the correct answer. Why those steps work was considered optional, sometimes even inconvenient. Understanding slowed things down. Efficiency mattered more. And slowly, math stopped being a way to see the world clearly and became a way to survive exams. This creates a dangerous illusion. People who can manipulate symbols fluently are assumed to understand what they represent. But fluency is not comprehension. You can recite a sentence in a foreign language without knowing what it means. Mathematical symbols are no different. Without intuition, they're just shapes on a page. When math becomes decoration, it gains authority without accountability. Complex equations intimidate people into silence. If something is expressed mathematically, it must be true, right? Not necessarily. Math can hide nonsense just as effectively as it can reveal truth. In fact, it's better at hiding nonsense because it looks precise even when the assumptions underneath are rotten. Real mathematical understanding is grounded in physical intuition, logical structure, and clear definitions. You should be able to say what each term means, what would happen if it changed, and why it must be there. If you can't explain what an equation is about, then solving it is meaningless. You're solving puzzles, not problems. This obsession with form over meaning disconnects math from reality. Students learn techniques but never learn how to model the world. They can differentiate and integrate but can't explain what's changing or why accumulation matters. They can solve differential equations yet have no sense of the behavior those equations describe. The map has replaced the territory, and when math loses contact with reality, it becomes fragile. The moment conditions change, the method fails. People don't know how to adapt because they never understood the structure in the first place. They learned the dance, not the music. There's also a psychological cost. When math is taught as decoration, people conclude they're bad at math. What they really mean is they're bad at memorizing rituals without meaning. Anyone would struggle under that system. Understanding is empowering. Memorization is alienating. Math was never meant to be mystical. It was meant to be clear. It's supposed to reduce confusion, not create it. The beauty of mathematics comes from insight, seeing why something must be true, not just that it is. When you strip away meaning, you also strip away beauty. The solution isn't to simplify math into something shallow, it's to reconnect symbols to ideas, to ask constantly, what does this represent? What assumption am I making? What would break if this term disappeared? Those questions turn decoration back into meaning. Math earns its power when it explains something you couldn't see before, when it predicts behavior, when it exposes hidden relationships. Without that, it's just impressive handwriting. Symbols should serve understanding, not replace it. When math stops meaning something, it stops being math at all. Authority replaced curiosity the moment we started as king who said it instead of why it's true. The shift was subtle at first, almost reasonable. Experts exist for a reason. Experience matters. Knowledge accumulates, but somewhere along the way, respect for expertise quietly mutated into obedience, and curiosity, the engine of understanding, was pushed aside as inefficient, even dangerous. Curiosity is slow. It asks uncomfortable questions. It challenges settled ideas. Authority, on the other hand, is convenient. It gives answers without demanding effort. When an authority speaks, thinking feels optional. You can stop exploring and start accepting. That trade-off feels harmless until you realize what it costs. The ability to tell the difference between truth and confidence. The problem isn't authority itself. The problem is unexamined authority. When ideas are accepted because of their source rather than their substance, thinking becomes passive. People learn conclusions without learning the reasoning that produced them. And once the reasoning is gone, the conclusion becomes fragile, defended, not understood. This is how dogma is born. Not from malice, but from comfort. Questioning takes energy. It risks embarrassment. It can make you look ignorant or disrespectful. So people learn to stay quiet. They learn that repeating the accepted answer is safer than asking an honest question. Over time, the questions stop forming altogether. When curiosity disappears, progress slows to a crawl. New ideas don't come from obedience. They from people who notice cracks in explanations and refuse to ignore them. Every major leap forward began as a question that authority couldn't answer or didn't like being asked. Authority also has a dangerous side effect. It shifts responsibility. If an idea comes from someone powerful, criticizing it feels risky. If it fails, blame is diffused. That's what the experts said. But understanding doesn't outsource responsibility. When you understand something, you're accountable for it. You can defend it, modify it, or abandon it based on evidence. Authority offers no such flexibility. There's another cost we rarely talk about. When authority replaces curiosity, learning becomes hierarchical instead of exploratory. Knowledge flows downward, not outward. Students wait to be told what matters instead of discovering it. They learn to optimize for approval rather than truth. The goal becomes agreement, not understanding. This environment rewards confidence over clarity. The person who speaks decisively, even without depth, is trusted more than the one who hesitates thoughtfully. Curiosity often sounds like uncertainty, and uncertainty is mistaken for weakness. But uncertainty is where real thinking lives. Certainty without examination is just a loud guess. Nature doesn't recognize authority. Reality doesn't check credentials. It responds only to what actually works. You can cite the most respected source in the world, but if the idea doesn't match reality, it will fail, quiet, lie, or catastrophically. Curiosity is what keeps us aligned with reality. It forces constant testing, constant adjustment. The tragedy is that curiosity is natural. Children are relentless questioners. They don't care who said something, they want to know how it works. Authority teaches them to stop. It teaches them that some questions are inappropriate, some ideas are settled, some lines shouldn't be crossed. And in doing so, it trains compliance, not intelligence. Respect for expertise should sharpen curiosity, not replace it. True understanding demands both, learning from those who know more while never surrendering the right to ask why. The moment you're forbidden from questioning, you're no longer learning, you're being managed. Curiosity is not rebellion for its own sake. It's loyalty to truth over comfort. Authority that cannot tolerate curiosity is not protecting knowledge, it's protecting itself. When authority replaces curiosity, thinking becomes fragile. When curiosity challenges authority, understanding grows stronger. Reality doesn't care about our theories, and that's the most uncomfortable truth the thinking mind has to accept. It doesn't care how elegant the model is, how famous the person who proposed it was, or how many people believe it. Reality has no interest in our explanations. It only responds to what actually happens. You can argue with people. You can't argue with nature. Theories are tools, not truths. They are guesses, sometimes brilliant, sometimes less crude, about how the world behaves. When they work, we keep them. When they fail, reality doesn't negotiate. It doesn't offer partial credit for effort or intent. It simply exposes the gap between what we thought and what is. The danger begins when we forget this. When a theory starts to feel sacred, questioning it feels like betrayal. People defend it, patch it, reinterpret failures instead of confronting them. But every time we protect a theory from reality, we weaken our understanding. We trade accuracy for comfort. Reality is ruthless but fair. It applies the same rules to everyone, everywhere, every time. If a bridge collapses, it doesn't matter how confident the engineer was. If a prediction fails, it doesn't matter how respected the theory is. Nature keeps the score, and it never lies. This is why prediction matters more than explanation. Anyone can explain the past after it's happened. Real understanding shows up when you can say what will happen next and be right. A theory that cannot risk being wrong is not a theory, it's a story. Our attachment to theories is emotional, not logical. We invest time, identity, and reputation into them. Admitting they're wrong feels like admitting personal failure. So we rationalize. We add exceptions. We adjust definitions. We protect the idea instead of testing it. Reality doesn't care. It keeps producing results that don't match. Progress happens only when we let theories die. Not because they were stupid, but because they incomplete. Every useful theory is a temporary one. The moment you believe your current explanation is final, you've stopped learning. This is also why authority and consensus can be dangerous when they replace evidence. 1,000 people agreeing on a wrong idea doesn't make it less wrong. Reality doesn't count votes. It doesn't reward popularity, it rewards alignment. Theories should make you humble. They are approximations, lenses through which we see part of the truth. Confusing the lens for reality itself is how errors persist. When observations don't fit, the lens must change, not the world. There's a strange freedom in this. If reality doesn't care about our theories, then being wrong is not shameful. It's expected. Wrong theories are not failures. They're data. Each mismatch is a clue pointing toward a better understanding if you're willing to listen. But listening requires discipline. It requires the courage to say, this doesn't work, to let go of ideas you like, to resist the temptation to explain away inconvenient facts. That discipline is the difference between science and belief. Reality is the final referee. It doesn't applaud cleverness. It doesn't respect intention. It only responds to cause and effect. Align with it and your ideas survive. Ignore it and they collapse. Eventually, always. Our theories are maps. Reality is the territory. Confuse the two and you get lost.
Try to imagine nothing. Go ahead. Close your eyes and try to visualize absolute emptiness. You probably see a black void, maybe some stars in the distance if you're feeling romantic, but essentially you picture a vacuum. You think of space as a stage, a big empty box where stuff happened. You put a planet here, a star there, maybe a confused astronaut floating in the middle. But the space itself, to you, it's just the container. It's the absence of things. I hate to break it to you, but that container doesn't exist. The idea of empty space is the greatest hallucination of the human mind. The universe isn't a box, it's a glob of jello. Okay, maybe not literal lime-flavored gelatin, but physically speaking, you are walking through a medium that is constantly being twisted, squashed, and pulled. When you look at the air in front of you, or the vacuum of space, you aren't looking at nothing. You are looking at a field. And until you understand what a field is, you don't understand physics. You're just memorizing rules for a game you don't know how to play. Let's start with something you can actually touch. Imagine a big, wobbling block of elastic material, a giant cube of jello sitting on a table. Now, suppose I reach in, grab a tiny speck of dirt trapped inside that jello, and I pull it. The jello distorts. It stretches. If you want to describe what happened to that block, you can't just say, it moved. That's lazy. You have to describe how every single point inside that block shifted relative to every other point. We call this strain. If I pull the corner, the middle moves a little, the far side moves barely at all, and the point under my finger moves a lot. To describe this mess, we need numbers, a lot of numbers. For every tiny point in that jello, we need to know how much it stretched sideways, how much it stretched upwards, and how much it stretched forward. And it gets worse. We need to know if it twisted. Did the top slide right while the bottom slid left? That's a shear. Suddenly, this innocent block of jello is a mathematical nightmare. To fully describe the stress and strain inside it, we can't just use a single arrow. We need a concept called a tensor, a beast of a mathematical object that packages all these stretches and twists together. But here's the beautiful part. This isn't just about jello. This is how the entire universe works. Physics is the business of assigning numbers to points in space. That's it. That's the job. If you assign a single number to every point in space, like, say, the temperature, you have what we call a scalar field. Imagine a block of metal that's hot on one side and cold on the other. You can close your eyes and point to any spot inside that metal, and there is a specific number waiting for you, 20 degrees. Move an inch left, 25 degrees. The temperature doesn't jump around randomly. It changes smoothly. It forms a landscape. Now, imagine drawing lines connecting all the points that have the exact same temperature. You get these invisible surfaces, like the contour lines on a topographic map. We call them isotherms. They are imaginary, but they tell you the shape of the heat. But a single number isn't enough for the interesting stuff. Sometimes, the universe has an arrow at every point. Think about a rotating object, or water flowing in a river. At every single point in that river, the water has a speed, but it also has a direction. It's going somewhere. You can't just say, the water is moving at 5 miles per hour. You have to say, 5 miles per hour downstream. This is a vector field. Imagine the room you are sitting in right now. The air seems still, but it isn't. There are tiny currents everywhere. If you could freeze time and attach a tiny little red arrow to every molecule of air showing where it was going, the room would look like a porcupine.
That forest of arrows is a field. Heat flow works the same way. Heat doesn't just sit there. It flows from the hot spots to the cold spots. So, superimposed over your map of temperature numbers, there is a map of heat flow arrows. And here is the rule. The heat arrow always points downhill. It wants to get away from the hot zone as fast as possible. Now, we need a way to connect these two things, the temperature numbers and the flow arrows. How do we find out which way the heat will flow just by looking at the temperature map? We use a mathematical machine. We call it del, which is just a fancy name for a symbol that acts like a meat grinder for functions. You feed it the map of temperatures, and it chews it up and spits out a map of arrows. This operation is called the gradient, and it is exactly what it sounds like. If you are standing on a hillside in the pitch dark and you want to know which way is up, you feel around with your feet. You find the direction where the slope is steepest. That direction is the gradient. The gradient of the temperature tells you the direction of the hottest change. It tells you, if you want to get hotter, go that way. And the heat flow? It simply obeys the opposite of the gradient. It runs down the hill. But nature isn't satisfied with just flowing down hills. Sometimes nature likes to spin. Imagine you have a field of arrows that looks like a whirlpool. The arrows aren't flowing out from a center, they are circling around it. If you dropped a leaf in there, it wouldn't just move, it would rotate. To measure this swirliness, we use another operation called the curl. If the gradient measures the slope of the hill, the curl measures how much the field is twisting. It tells you the rotation. And then there's the divergence. This measures how much the stuff is spreading out. If you have a nozzle spraying water, the divergence is high at the nozzle because water is exploding outward. If you have a drain, the divergence is negative because water is vanishing into it. Why am I telling you about hills, swirls, and drains? Because these three concepts, gradient, curl, and divergence, are the language of reality. Maxwell's equations, the laws that govern light, electricity, are just sentences written in this language. They say things like, the divergence of the electric field is the charge. Translation, electric charge is a sprayer that shoots electric field arrows outward. Or, the divergence of the magnetic field is zero. Translation, there are no magnetic sprayers, no magnetic charges. Magnetic lines never start or stop. They just loop forever. Speaking of magnetism, this is where things get really weird. You think you know what magnetism is. You played with magnets as a kid. You know they stick to the fridge and hate each other if you flip them around. But have you ever asked why? Why does a wire carrying an electric current suddenly turn into a magnet? Let's look at the force on a moving charge. We call it the Lorentz force. It's the rule that says if you shoot a charged particle through a magnetic field, it gets pushed sideways. Not forward, not backward, sideways. It's a force that acts perpendicular to the motion. That's bizarre. Gravity pulls you down. Electrical attraction pulls you closer. But magnetism pushes you sideways, like a rude pedestrian shoving you into traffic. The standard explanation involves the right-hand rule. You hold up your hand, point your thumb, curl your fingers, and look like you're trying to hail a taxi while doing yoga. It works, but it's arbitrary. Nature doesn't have hands. Here is the truth. Magnetism is not a separate thing. It's just electricity seen from a moving perspective. Imagine a copper wire. Inside, you have positive copper ions fixed in place, and a sea of negative electrons flowing through them like a river. This is the current. Now, imagine a single negative charge moving alongside this wire at the exact same speed as the electrons inside the wire. From your perspective, standing still in the lab, you see a current. You check your rule book and it says, currents create magnetic fields. Okay? The magnetic field pushes the moving charge toward the wire. Simple. But wait. Let's look at it from the perspective of the moving charge. If you are the charge, you are looking at the electrons in the wire, and they look stationary relative to you because you're moving at the same speed. If they are stationary, there is no current. If there is no current, there is no magnetic field. So, if there is no magnetic field, the force disappears, right? The charge should drift away? Wrong. The charge still gets pushed toward the wire. But how? If the magnetic force vanished, what is pushing it?
Einstein steps in. You see, when things move, space itself contracts.
It squishes. This is special relativity. From the perspective of our moving charge, the positive ions in the wire, which were stationary in the lab, are now rushing backward. Because they are moving, the distance between them shrinks. They get packed denser. Meanwhile, the electrons in the wire, which are moving with us, appear stationary. Their spacing relaxes. They spread out. Do you see what just happened? The wire, which used to be electrically neutral, now has a higher density of positive charges and a lower density of negative charges. To the moving particle, the wire has suddenly become positively charged. It's not magnetism pulling the particle in, it's good old-fashioned electric attraction. The particle sees a positively charged wire and wants to hug it. So, what we call a magnetic field in the lab is just an electric field disguised by relativity. It's what happens to electricity when you start moving. This connects back to our vector fields. We said earlier that fields define the force on a charge. We have an electric field vector and a magnetic field vector. What we just discovered is that these aren't two different actors. They are the same actor changing costumes depending on how fast you run past the stage. If you stand still, you see electricity. If you run, you see a mix of electricity and magnetism. They are components of one giant four-dimensional object, the electromagnetic field. But there is a catch. To make this work, charge has to be indestructible. Think about the conservation of charge. It's a fancy way of saying charge is conserved. You can't create electrons out of nothing, and you can't make them vanish. If a current flows out of a box, the amount of charge inside the box must go down. It's basically accounting. If charge wasn't conserved, if it could change depending on your speed, the whole universe would break. Imagine heating up a block of metal. The electrons speed up. If their charge changed because of that speed, the block would suddenly become electrically charged just because it got hot. Massive sparks would fly every time you made toast. Since your toaster doesn't kill you, usually, we know charge is an invariant scalar. It's the same number no matter how fast you go. Now, let's go back to those magnetic field lines. Remember, the divergence of the magnetic field is zero. No magnetic charges. This means magnetic field lines have to form closed loops. They are like rubber bands that never break. If you have a straight wire, the field lines circle around it. If you have a loop of wire, the field lines thread through the middle and wrap around the outside, looking like a donut. This creates the magnetic dipole. It's the basic unit of magnetism. You don't have a north pole and a south pole sitting separately. You have a loop. The north is just the side where the lines come out, and the south is where they go in. But here is a question that should bother you. Where do the lines go when they hit the end of a bar magnet? They don't stop. They go through the magnet. A permanent magnet is just a solenoid that doesn't need a battery. Inside that iron bar, billions of tiny electrons are spinning. Each spinning electron is a tiny current loop. In iron, these loops decide to line up and sing in the same choir. The result is a macroscopic magnetic field. So there is no magic magnetic fluid inside the iron. It's just currents, permanent atomic currents that never stop flowing. But we are still describing this with lines and loops. Is that what's really there? Are there invisible spaghetti strings filling the room? Of course not. The lines are just a drawing tool. What's really there is something called the vector potential. And this is where we have to abandon the high school pictures entirely and look at the machinery under the floorboards. Because it turns out the magnetic field might just be a shadow of something more fundamental, something we call A. We left off with a cliffhanger. We stripped away the magnetic field lines and realized they are just cartoons. We realized that magnetism and electricity are the same thing, just viewed from different speeds. But if we want to actually predict what the universe will do next, if we want to see the machinery under the floorboards, we need to talk about the ghost. We need to talk about A. In the simple world of electrostatics, life is easy. You have a scalar potential, voltage. It's like height on a topographic map. If you know the voltage everywhere, you just roll the ball down the hill, and that's your electric field. Simple, intuitive. But magnetism is a headache. It doesn't act like a hill. It acts like a whirlpool. It swirls. So we can't represent it with a simple scalar number like height. We need something with direction. We need a vector potential. We call it A. Think of A as the momentum of space itself. Imagine a river. The water is flowing. That flow is A. If you drop a leaf in the river, it moves with the flow. But if you stick a paddle wheel in the river, it spins. That spin, that's the magnetic field. The magnetic field B is just the turbulence that happens around the edges of the flow of A. For a long time, physicists thought A was fake. They thought it was just a bookkeeping trick, a mathematical shortcut to calculate the real magnetic field. But then quantum mechanics came along and ruined the party. It turns out you can shield a particle from the magnetic field completely, hide it behind a lead wall where the magnetic field is zero, and the particle still feels something. It feels the river of A flowing past the wall. The ghost is real. In fact, the ghost is more fundamental than the thing it haunts. The vector potential is the primary fabric of electromagnetism. The magnetic field is just its derivative. Now I want to pivot. We've been talking about fields as if they are these ethereal, magical clouds hanging in the void. But to truly understand the vacuum, you need to stop thinking of it as a cloud. You need to think of it as a solid object. You need to go back to the jello. When engineers study solid materials, steel, concrete, rubber, they use a branch of physics called elasticity. And when we study the vacuum of empty space, we find the exact same mathematics. Consider that glob of jello we talked about. Suppose you twist it and squash it. To describe the internal torture of that jello, you can't just say it's under pressure. Pressure is too simple. It pushes everywhere equally. But in a solid, you can push on one face while pulling on another. You can twist the top while holding the bottom still. We describe this internal mess with a stress tensor. Don't let the words scare you. A tensor is just a box of numbers. If a vector is an arrow, a tensor is a machine that takes an arrow and twists it. The stress tensor tells you exactly how much force is acting on every possible surface inside the material. It tells you, on the top face, we are pushing right. On the side face, we are pulling down. And how does the material respond to this stress? It deforms. We call this strain. If a tiny speck of dust inside the jello moves from point A to point B, that's displacement. But strain is subtler. Strain measures how the neighbors of that speck moved relative to it. Did they get closer? Did they drift apart? Did they rotate around it? This is defined by the strain tensor. It's the map of the distortion. Why am I talking about engineering concepts in a script about the universe? Because energy doesn't care what it's made of. When you squeeze a spring, you store energy. When you shear a block of metal, you store energy. The amount of energy stored depends on a very simple rule. Stress times strain. How hard you push, multiplied by how much it moves. This is true for a rubber band, and it is true for the vacuum of space. An electric field is a stress. A magnetic field is a strain. The empty space between the stars is loaded with potential energy. Stored in the electromagnetic fields exactly like elastic potential energy is stored in a twisted steel beam. This is why light exists. If you kick a block of steel, a wave travels through it. We call it sound. The speed of that sound depends on two things: how stiff the material is, how hard it fights back, and how heavy it is, how hard it is to move. If you kick the vacuum, a wave travels through it. We call it light. And the speed of light? It is determined by the stiffness of the vacuum and the density of the vacuum.
You have probably seen the constants epsilon 0 and mu 0 in physics textbooks. They look like boring numbers. They are not. They are the elastic constants of the vacuum. One tells you how hard space fights back against electric stress, stiffness, and the other tells you how much magnetic inertia it has, density. Light travels at c, not because it's a cosmic speed limit imposed by the police, but because that is the speed of sound in the solid block of nothingness we call the universe. But here is where the analogy gets really fun. Real materials aren't perfect. If you pull a spring too hard, it snaps. Take a piece of blackboard chalk. If you hold the ends and pull, it snaps in half. If you look at the break, it's a clean, flat cut perpendicular to the pull. Why? Because chalk is brittle. It is weak in tension. It cannot handle being pulled apart. But now, take another piece of chalk and twist it.
It doesn't snap straight across. It breaks in a spiral at a 45-degree angle. It looks like a corkscrew. Why? You didn't pull it, you twisted it. You applied a shear. But the math of tensors reveals a secret. A shear is just a tension in disguise. When you twist the chalk, you are actually creating a line of maximum tension running at 45 degrees along the surface. The chalk finds this hidden tension and snaps exactly along that line. Nature is full of these hidden mechanisms. The geometry of the stress dictates the geometry of the failure. Does the vacuum of space have a breaking point? Can you pull on the electric field so hard that space itself snaps? In classical physics, no. But in quantum electrodynamics, yes. If you create an electric field strong enough, a critical field, you can literally rip particles out of the vacuum. You can tear the nothing apart and create electrons and positrons out of pure stress. The vacuum isn't just a stage. It's a material that can be stressed until it breaks into matter. So, let's revisit our opening question. What exists between the object? The answer is everything. The quantum vacuum is not empty space. It is a plenum. It is a solid medium. It is a playground of fields described by vectors, scalars, and tensors. It has a temperature. It has a flow. It has stiffness. It has inertia. It has momentum. It can be twisted, sheared, and stressed. It stores energy. It carries waves. Understanding physics isn't about memorizing that gravity pulls or magnets attract. It's about learning to see the invisible scaffolding. It's about realizing that a differential equation isn't just algebra. It's a set of instructions for how the jello wobbles from 1 millimeter to the next. Einstein didn't invent a new language to describe gravity. He just borrowed the language of geology and structural engineering. He looked at the universe and realized that space-time is just a giant, bendable solid, and gravity is just the strain tensor of the cosmos. So, the next time you look at the night sky, don't see emptiness, don't see a void, see the fields, see the tensors stretching and squeezing in the dark, see the huge invisible river of vector potential swirling around every wire and every atom. The universe is a crowded place, and the nothing is the heaviest thing in it.
Push two magnets together. Feel that something invisible is fighting you, pushing back against your fingers. Now, flip one around. Snap. They slam. Together so violently you almost lose a fingertip. What just happened? What invisible thing is out there in the empty air between two pieces of metal? Strong enough to hurt you? You felt this your entire life, and I'm about to tell you something that'll make you question every solid object you've ever touched, because the answer, it's not what you think. And by the end of this, you're going to realize you've never actually touched anything in your entire life. Let me show you how deep this goes, T. But first, we need to talk about a problem, because when you ask why about anything, you're walking into a trap. Here's what I mean. Why is your aunt, Minnie, in the hospital? She slipped on ice and broke her hip. Simple enough, right? But why did she slip? Ice is slippery. Everyone knows that, but why? Is ice slippery? Now it gets interesting. When you stand on ice, the pressure from your weight melts a microscopic layer on top. You're not slipping on ice at all. You're slipping on water. Okay, but why does pressure melt ice? Because water does something bizarre. It expands when it freezes. Almost nothing else does this. So pressure wants to reverse that. Expansion, turning it back to liquid. But hold on, why does water expand when it freezes in the first place? And wait, why did she fall when she slipped? That's gravity. Now you're suddenly talking about planets and the entire structure of the universe. Why does falling hurt? Why did her husband call the hospital? Because he cares about his wife. But does he, though? Not all. Husbands do when they're drunk and angry. See what just happened? Every single answer opened 3 more questions. You could keep asking why until you collapse from exhaustion. You have to stop somewhere or you'll be falling forever. And this is exactly what happens when people ask me to explain magnets. People want me to explain magnets using something they already understand, something familiar. Maybe it's like invisible rubber bands, connecting them, pulling them together. And sure, I could tell you that. You'd be satisfied for about 3 seconds. Then you'd ask, okay, but why do rubber bands pull back? And now I'd have to explain forces between molecules, which are electrical forces, which are the Exact same forces I'm trying to explain with the magnets in the first place. I'm running in circles using the mystery to explain the mystery. That's not understanding. That's a con game. Here's the truth. Electrical and magnetic. Forces are fundamental. They're bedrock, the bottom of the well. We don't explain them in terms of something else. We explain everything else in terms of them. Chemistry, that's electromagnetic. Forces between atoms. Biology built on chemistry, which means it's built on electromagnetism, the chair holding you. Up right now, electromagnetic, your entire body not falling apart into a cloud of atoms. Electromagnetic, it's everywhere, it runs everything. But here's where it gets weird. You don't think it's strange that you can't push your hand through a table, do you? You push on it. It pushes back. Totally normal. You've done it 10,000 times. But your hand never actually touches the table. No, I'm serious. The atoms in your hand get close to the atoms in the table and the electrons start repelling each other. That repulsion, that's what you feel is solid, that sensation you call touching. That's the exact same. Forces, the magnets, identical, the same physics, the same interactions at the atomic level. So why does the table seem obvious and the magnets seem mysterious? Only because you grew up pushing on tables every single day and not pushing magnets together. The table is just as strange. You just stopped wondering about it. And this leads us to something absolutely mind-blowing about how strong these forces really are. Electrical forces aren't just strong, they're monstrously, absurdly, incomprehensibly strong compared to gravity. Electromagnetism is stronger by a factor of about 1 followed by 40. Zeros, I don't even know what to call that number. It's not in my vocabulary. This isn't much stronger. This is so much stronger that it doesn't make sense. So why don't we notice? Because atoms are balanced, positive charges in, the nucleus, negative charges orbiting around the outside, plus and minus, everything neutralizes. The most powerful force in the universe is hiding in plain sight because it cancels itself out. But watch what happens when you create even the tiniest imbalance. Comb your hair on a dry day and hold it near some bits of paper. The paper jumps up. To meet the calm, you rubbed off a few electrons, just a few, maybe a trillionth of the total. But the electromagnetic force is so gigantic that even that microscopic imbalance creates something you can see from across the room. Now imagine what happens when you don't let things cancel out, when you force all those tiny effects to line up and work together. Instead of fighting each other, that's where magnets come in. Magnets are special because of what happens inside. Iron, every electron spins. They all do this. It's a fundamental property. In most materials, those spins point which way? Complete chaos. North, south, east, west, up, down. They all cancel each other out and you get nothing. But in iron, they line up. All those electrons spinning in the same direction. And when they cooperate like that, when they work together, all those tiny magnetic effects stop canceling, they add up, they amplify. Suddenly, you've got something you can feel from across the room. That's why iron is magnetic and copper isn't. Copper has the same physics, the same electrons, the same forces, but the spins point randomly. In iron, they're an army marching in formation. Think of it like a stadium full of people. If everyone talks at once, you hear nothing but noise. But if everyone chants the same word together, you can hear it miles away. Same voices, completely different effect. But this is where it gets really interesting because we can go deeper. We can ask what's actually happening at the most fundamental level when two magnets pull toward each other. And the answer is going to sound insane. At the most fundamental level, it's about particles being exchanged. Electrons don't just sit there staring at each other. They're constantly throwing things back and forth. Photons, little packets of light. And I don't mean light you can see. These are what we call virtual photons. They exist only during the interaction. You can never catch one and examine it directly. It's there and gone. One electron throws a photon, another electron catches it. And that exchange, that endless game of catch happening trillions of times per second, that's what you experience as the electromagnetic force. It sounds bizarre, right? Two things pushing or pulling each other by throwing invisible stuff back and forth. But that's exactly what's happening every time you feel a magnet push against another magnet. Trillions upon trillions of these virtual photons are being exchanged between the electrons in both pieces of metal. And here's the beautiful thing, everything, and I mean everything, electromagnetic comes from just three simple actions. One, a photon goes from one place to another. Two, an electron goes from one place to another. 3. An electron emits or absorbs a photon. That's it. 3 actions. From those 3 actions, you get all of chemistry, all of light, all of magnetism, all of electricity, radio waves, the colors you see, the fact that your hand stops at the table instead of passing through it, like a ghost, all of it. There are no Gia, RS underneath, no hidden mechanism waiting to be discovered. This is how it really works. But hold on, this changes everything about what we thought we knew. In 1873, a physicist named Maxwell wrote down a set of equations. These equations unified electricity and magnetism into a single phenomenon. They're 2 faces of the same thing. This was probably the most fundamental transformation in human history, because once you understand that electrical and magnetic forces are connected, you can do things. You can make a current and a wire create a magnetic field. You can move a magnet near a wire and create a current back and forth. Electricity and magnetism dancing together. Think about what this means in practice. There's a dam somewhere far away. Waterfalls. Turns a big wheel. That wheel is connected to copper wires spinning near some magnets. Because the copper moves through the magnetic field, electrons start flowing through the wire. That flow of electrons travels through thin copper cables stretched across hundreds of miles through your entire city. And at the other end in your house, another piece of copper and iron converts that electron flow back into spinning motion. Your fan turns, your refrigerator hums, your lights glow. All the wheels in the city turn because one wheel at the dam turned, stopped that one. Everything stops, started again. Everything starts. And what's doing this? Just copper and iron, nothing else. It's not complicated machinery. It's not some special exotic substance. It's just the fundamental nature of electromagnetism. You move magnets here. Electrons flow through copper. Magnets move over there far away, connected by nothing but wire. What an absolutely fantastic thing nature is. But the precision with which we understand this, that's where things get truly remarkable. We can calculate how magnetic an electron is, not guess, not estimate, calculate, using just those 3 simple actions. Photon goes here, electron goes there, electron absorbs, photon. You add up all the different ways these interactions can happen, all the possible paths, and you get a number when you measure what nature actually does with extremely precise instruments. The theory and the experiment match to an extraordinary degree. How extraordinary? The difference between our prediction and what we measure is so small. It's like measuring the distance from Los Angeles to New York and being accurate to less than the thickness of a human hair. That kind of precision doesn't exist anywhere else in science. This is the most accurate prediction humans have ever made about anything. And it comes from understanding the electromagnetic force, the same force you felt as a kid pushing 2 magnets together so we can describe magnetism with spectacular precision. We can predict exactly what it will do. But can we explain why it exists in terms of something more familiar? No, and that's not because we failed. That's because electromagnetic forces, are the familiar thing that explains everything else. But there's a problem, a mystery at the heart of all this that nobody can solve, appears everywhere. It's run thirds everywhere. It's roughly 137, or if you want to be more precise, it's about Joe. 1097, 56, 93, which is approximately 5th. 37, this number determines how strong the electromagnetic force is, how strongly magnets attract, how much. Electrons repel each other. Everything about electricity and magnetism depends on it, and nobody knows where it comes from. We didn't calculate it from something deeper. We didn't derive it from first principles. It just is that number. If you ask why 137 and not 200 or 50, there's no answer. It's one of the great damn mysteries of physics. Where did this number come from? Did somebody write it down somewhere? And we just haven't found it yet. If that number were very different, magnets would be stronger or weaker. Atoms wouldn't hold together the way they do. Chemistry would change completely. We probably wouldn't exist. The whole universe, including every magnet you've ever touched, depends on this mysterious 137, and we have no idea why. But the history of how we figured even this much out, that's a story of near failure and mathematical desperation. When physicists first tried to calculate the magnetic properties of electrons using quantum theory, they got nonsense, infinity. The equations gave infinity, not a really big number actual. Mathematical infinity, that's not an answer, that's a breakdown. For years, people struggled with this. The math seemed fundamentally broken, then around. 1948, a solution appeared. The idea is this. We never measure a bare electron by itself. What we actually measure is the electron plus all its interactions, all those virtual photons being exchanged constantly. So you start from what you can actually measure in experiments and the infinities get. Absorbed into those measured quantities, everything comes out finite. It's called renormalization. Some physicists think it's suspicious, like we're hiding the problems under a mathematical rug. But the results match experiments too. Incredible precision, those 10 decimal places we talked about. So maybe that's just how nature is. Maybe asking about the bare electron without its cloud of interactions is like asking what a person looks like without their personality. It's a wrong question, but this leads us to an uncomfortable truth about understanding at the deepest level. Here's something I need to be honest about. The way quantum mechanics works, it's nothing like everyday experience. Your brain evolved to understand rocks and trees and animals, things at human scale, things you can throw and catch. But electrons don't behave like tiny balls. They don't orbit. The nucleus like miniature planets. People say electrons act like waves. Not exactly like particles. Not exactly like a cloud or fog. No, that's not right. Either, if you want a clear mental picture of what's happening inside a magnet at the atomic level, something you can visualize, something you can see in your mind. I can't give you one, nobody can. What we have is mathematics. We write equations, we calculate, and predictions match reality with extraordinary accuracy. It's like having a perfect calculator that tells you exactly when and where something will happen. It does the arithmetic flawlessly, gives exact answers, but it has no picture in its head, no visualization, no image. It just calculates. That's where we are with quantum mechanics. We calculate what magnets will do. We're extraordinarily good at it, better than almost anything else in science. But the intuitive picture, the ability to really see what's happening that's beyond us, nature at that scale is genuinely different from anything we evolved to understand. And that brings us back to where we started. You push two magnets together, you feel that force in you. Ask the honest answer. It's electrons exchanging virtual photons. It's electron spins lining up in iron. It's the electromagnetic force that holds your entire body together and runs the whole universe. We can describe it with spectacular precision, accurate to 10 decimal places, but if you want me to, explain it in terms of rubber bands or springs or anything else you are ready. No, I can't, because those things are explained by electromagnetism, not the other way around. Magnetism isn't the mystery that needs explaining. Magnetism is the explanation. Magnetism isn't some strange, isolated phenomenon happening in certain pieces of metal. It's part of the electromagnetic force, one of the four fundamental forces of nature. Every atom in your body is held together by it. Every chemical reaction depends on it. When you see colors, that's electromagnetism. When you touch something solid, that's electromagnetism. When a compass points north, when a motor spins, it's all the same force, and it emerges from just three simple actions. A photon goes from here to there, an electron goes from here to there, an electron emits or absorbs a photon. Three things, that's it. Chemistry, biology, the structure of matter, it all emerges from these three actions combining in countless ways. There are no gears underneath. There's no deeper mechanism hiding behind it, all waiting to be discovered. Now, does that mean we understand everything? No. That mysterious number, 137, nobody knows where it comes from. We can't picture what electrons actually do at the quantum level. We describe nature with mathematics that works beautifully, but our mental images are always approximations, shadows on the wall. But here's the thing about physics. It's experimental. You don't sit around waiting to understand everything perfectly before you do anything. You learn enough to predict what happens. You test it, and if it works, you use it. That dam with copper, wire-making wheels turn across the entire city. That works because we understand electromagnetism well enough, not perfectly, well enough. When you asked why magnets attract, you wanted an answer in terms of something familiar. Rubber bands, springs, invisible strings, pulling things together. But The answer is that magnetism iced the familiar thing. You just didn't realize it. Every time you've touched anything in your entire life, you've been feeling electromagnetic forces. Every solid object, every surface you've ever leaned against, that's electrons pushing against electrons. You've been swimming in electromagnetism since the day you were born. Magnets just make it obvious. They let you feel at a distance what's usually hidden at microscopic scales. So next time you pick up a magnet and feel that push or pull, don't think of it as mysterious. Think of it as nature, being honest with you for once, showing you directly what's usually invisible, the same force that holds your own hand, together acting across the empty space, between two pieces of iron. That's what's happening. That's what you're feeling. And the fact that we can describe it, predict it, calculate it.
Richard Feynman's IQ was 125, respectable, but unremarkable. At the Manhattan Project, he sat alongside men with IQs over 180. John von Neumann, the mathematician who could perform calculations faster than early computers, IQ estimated at 190. J. Robert Oppenheimer, the theoretical physicist directing the entire operation, IQ north of 180. Edward Teller, the hydrogen bomb architect, certified genius by every metric. By every conventional measure, Feynman was the least intelligent person in the room. His 125 IQ came from Far Rockaway High School aptitude testing, a score he mentioned dismissively in later interviews, almost embarrassed by its ordinariness. Yet within months of arriving at Los Alamos in 1943, something peculiar happened. Senior physicists began lining up outside Feynman's office, not because of his credentials, not because of test scores, because when the hardest problems emerged, when equations refused to surrender, when brilliance alone failed, Feynman had answers. That the certified geniuses missed, the reason why destroys everything you believe about intelligence. Society teaches us intelligence is speed, higher IQ, faster processing, quicker pattern recognition. Schools reward those who memorize fastest. Corporations hire from prestigious universities. Online courses promise master Python in 21 days or learn AI in one weekend. This creates a culture that worships shortcuts and venerates genetic intellectual gifts. Walk into any tech company and listen to engineers compete over algorithm speed, prestigious degrees, LeetCode code scores solved under time pressure. The message is clear: fast equals smart. This produces a specific problem. Speed without understanding creates brittle knowledge. Fast thinking misses deep patterns. Credentials substitute for capability. You can memorize React syntax from tutorials and still freeze when the framework updates. You can hold AWS certifications and panic when systems fail in unexpected ways. You can test at genius level and plateau while slower thinkers advance past you. The high IQ trap is real, documented, and career-destroying. Feynman did the opposite. He thought slower. He rebuilt concepts from scratch. He refused to memorize formulas that other physicists accepted as settled truth. While colleagues raced ahead, Feynman stayed behind, reconstructing, questioning, playing with ideas like a child assembles blocks. This approach looked inefficient. His professors worried. His peers dismissed him as plodding. But this produced a different result: deep, transferable understanding that worked across any problem. Slow thinking that outlasted fast intelligence. As documented in James Gleick's biography, Genius, The Life and Science of Richard Feynman, this wasn't personality quirk. It was deliberate method, practiced across 5 decades, refined into a system that beat genetic advantage every single time. To understand how someone with a merely good IQ beats certified geniuses, we need to see what he actually did differently, not what he had. What he practiced. MIT, 1939. Feynman is a graduate student in theoretical physics. The standard path is clear. Attend lectures, memorize equation tables, reference known solutions from textbooks, publish papers that extend existing work incrementally. The students around him, many with higher IQs, stronger test scores, better undergraduate credentials, follow this path efficiently. They check textbooks immediately when assigned problems. They memorize standard techniques. They optimize for speed. Feynman refuses. His advisor, John Wheeler, assigns him a quantum electrodynamics problem involving particle interactions. Other graduate students solve it in hours by checking reference materials. Feynman sits with blank notebooks. He spends 3 full days deriving the answer from scratch, starting from Maxwell's equations of electromagnetism and building upward, line by line, refusing to skip steps or reference shortcuts. Wheeler notices something unusual. Feynman's final solution differs slightly from the textbook answer, but it's correct. More importantly, Feynman can now solve any related problem because he understands the foundation. When Wheeler assigns variations, Feynman adapts instantly. The textbook memorizers can only solve problems identical to examples they have seen. New configurations break them. This reveals something about how intelligence actually works. High IQ provides faster pattern matching against existing templates stored in memory. But physics problems don't repeat exactly. They mutate. Variables shift. Context change. Memorization breaks. Reconstruction adapts. Feynman later explained his approach in "Surely You're Joking, Mr. Feynman." I had a scheme, which I still use today when somebody is explaining something that I'm trying to understand. I keep making up examples. Not memorizing their examples, creating his own. This forces reconstruction rather than recognition. While high IQ, students optimized for speed, memorizing proven formulas. Feynman optimized for understanding, reconstructing logic chains from axioms. His slowness was actually depth. He spent 3 days where others spent 3 hours. But those 3 days built a mental model that worked for 3 decades. The fast students had to rememorize for every new problem type, constantly updating their mental libraries. Feynman never had to update. His foundation didn't change because it was built from principles, not patterns. The same principle applies today when you're learning to code. If you memorize PyTorch syntax from tutorials, you'll freeze when the library updates or when you need TensorFlow instead. If you reconstruct how neural networks actually work from calculus and linear algebra fundamentals, you'll adapt to any framework. The fast path looks efficient initially. The slow path compounds over years. When you're studying for technical certifications, AWS, Azure, Kubernetes, the choice is identical. Memorize enough to pass the test, and you'll struggle with real-world scenarios the certification didn't cover. Understand the underlying distributed systems principles, and you'll solve problems the test writers never imagined. Feynman's method: refuse the shortcut. Build from ground zero. Think slower. Understand deeper. But reconstruction alone doesn't explain how he beat 180 IQ physicists. There's a second pattern, visible at Los Alamos. The Manhattan Project assembles the highest IQ concentration in human history. Von Neumann focuses on explosive lens calculations. Oppenheimer manages theoretical divisions. Teller pursues hydrogen bomb side projects. Senior physicists compete for prestigious assignments, bomb design calculations, theoretical papers that will secure post-war academic positions, work that carries historical weight. Feynman, the youngest group leader and lowest credentialed physicist, chooses differently. He volunteers for tedious problems that others avoid, checking calculations line by line, debugging integration errors, tutoring military technicians who lack physics backgrounds, working through simple mechanical problems that senior scientists consider beneath them. His colleagues see this as career suicide. Why waste time on computational grunt work when you could be advancing theoretical frontiers? But Feynman understands something they miss. These boring problems force him to understand every aspect of bomb physics. While von Neumann focuses narrowly on one mathematical specialty, Feynman learns everything: neutron diffusion, compression dynamics, detonation timing, metallurgy constraints, engineering tolerances. The high IQ specialists become experts in fragments. Feynman becomes expert in the complete system. Within 6 months, the consequences emerge. Integration problems arise, moments when separate systems must work together, and conflicts appear. Von Neumann's lens calculations conflict with Teller's. Compression estimates. Oppenheimer's theoretical models clash with engineering realities. Each specialist understands their piece perfectly, but can't see how pieces interconnect. Feynman sees it, not because his IQ is higher, because his problem selection strategy built broader, deeper models. Hans Bethe, the theoretical division leader, and himself a Nobel laureate, starts routing the hardest integration problems to Feynman rather than to higher credentialed physicists. As documented in Richard Rhodes' The Making of the Atomic Bomb, Beath considered Feynman more valuable than specialists with superior test scores because Feynman could cross boundaries that specialization created. This reveals a second principle. High IQ creates confidence and speed, which produces credential hunting, chasing prestigious problems, high-status assignments, impressive-sounding expertise that looks good on CVs. Feynman's method was opposite. Choose problems for learning, not status. Work on boring. Problems that teach fundamentals. Avoid narrow specialization that produces fragile expertise. This wasn't modesty. It was strategy. While 180 IQ physicists optimized for short-term prestige, papers, recognition, post-war positions, Feynman optimized for long-term capability. The result? When novel problems emerged, specialists were helpless outside their domains. Feynman adapted, not because his brain processed faster, because his learning strategy was wiser. The same principle applies when you're building career skills today. If you chase impressive-sounding roles, senior AI architect, principal blockchain engineer, without understanding fundamentals, you'll panic when technology shifts. These titles look spectacular on LinkedIn, but produce brittle expertise. If you deliberately work on boring foundation problems, data structures, system design, database internals, networking protocols, you build transferable mastery that works across any technology wave. When preparing for career transitions, the choice is identical. Don't optimize for what sounds impressive in job descriptions. Optimize for what teaches complete systems. The senior engineers who survive technology disruptions aren't those with the most prestigious past titles. They're those who understand foundations deeply enough to rebuild expertise in new domains. Work the problems others avoid because they seem tedious. That's where real understanding hides. But there's a third pattern, visible after the war. Cornell University, 1945. World War II ends. Physicists race to publish in the new quantum electrodynamics field. Speed matters. First publication wins credit, academic positions, research funding. The competition is fierce and explicit. Julian Schwinger, a physicist with IQ over 180 and Harvard pedigree, publishes complex mathematical papers quickly. His work is impressive, rigorously proven, mathematically elegant. It wins him immediate recognition and Nobel Prize consideration. But there's a problem. Almost nobody can understand or use Schwinger's equations. They're technically correct, but conceptually opaque. Only specialists can follow his logic. Feynman does the opposite. He spends 4 years developing his diagrams, simple pictures that represent particle interactions visually rather than mathematically. His colleagues grow impatient. Why waste time drawing pictures when Schwinger already solved the problem with equations? Publish or perish. The pressure builds. Feynman refuses to publish until he achieves perfect conceptual clarity. Not mathematical rigor, Schwinger already has that. Clarity. The ability for any physics student to grasp the underlying logic without specialized training. 4 years of refinement, simplification, playing with visual representations until complexity dissolves. Feynman finally publishes his diagrams. The physics community discovers something remarkable. Feynman's pictorial method and Schwinger's mathematical method produce identical predictions. Both are correct, but Feynman's method is teachable. Within years, every physics graduate student learns Feynman diagrams. Schwinger's equations remain historical footnotes studied only by specialists. Both men win the Nobel Prize in 1965 for the same discovery, but Schwinger's work dies with his generation. Feynman's diagrams become the standard method taught worldwide for 75 years and counting. Not because Feynman was smarter, because he prioritized clarity over complexity, simplicity over sophistication, teaching over impressing. In the Feynman Lectures on Physics, he articulated this philosophy. I couldn't reduce it to the freshman level. That means we really don't understand it. This wasn't false modesty. It was epistemological standard. Understanding means ability to explain simply. If explanation requires jargon and complexity, the explainer doesn't truly understand. They are hiding behind sophisticated language. High IQ produces fast, complex articulation, formulaic elegance, mathematical sophistication. This impresses peer reviewers but obscures understanding. Schwinger optimized for impressiveness, complex equations that signal intelligence to academic committees. Feynman optimized for clarity, simple pictures that signal understanding to students. The market rewarded Schwinger short term. He got prestigious positions, rapid publication, immediate recognition. Reality rewarded Feynman long term. His work became foundational. His method became universal. His legacy outlasted every rival. This reveals a third principle. Speed and complexity signal intelligence. Slowness and clarity signal mastery. The system rewards the former. Reality rewards the latter. The same principle applies when you're explaining your expertise today. If you use jargon and complex frameworks to sound smart in stakeholder meetings, you signal intelligence but hide ignorance. Anyone can make simple things complex. Mastery is making complex things simple. If you optimize presentations for impressiveness, dense slides, technical terminology, sophisticated models, you win short-term credibility from people who don't understand the domain. If you optimize for clarity, visual diagrams, plain language, concrete examples, you win long-term influence from people who need to act on your insights. When learning any new field, force yourself to explain concepts simply. If you can't draw the idea, you don't understand it. If you need jargon, you're hiding. Feynman's 4-year delay wasn't procrastination. It was the discipline of mastery, refusing to move forward until understanding was complete. But why did this work? What happens when you combine these 3 patterns? When you combine first principles reconstruction, plus deliberate problem selection, plus conceptual clarity, you get something more powerful than high IQ. You get method. Transferable, systematic, improvable method that compounds over decades. This is why Feynman won the Nobel Prize, not because his IQ was highest, but because his method was deepest. While faster minds chase speed, Feynman chased understanding. While certified geniuses competed for prestigious problems, Feynman chose problems for learning. While complex thinkers impressed peer reviewers, Feynman simplified until clarity emerged. The result: his diagrams became universal language spoken by every physicist worldwide. His lectures became the gold standard of pedagogy, still used 60 years later. His problem-solving approach outlived every high IQ rival who burned out, specialized into irrelevance, or published work that died with their generation. But this reveals something deeper about intelligence itself. Intelligence is not fixed capacity. It's not genetic lottery determined by childhood test scores. Intelligence is method multiplied by consistent practice over time. Von Neumann had IQ 190. He could multiply 4-digit numbers instantly in his head, speak 7 languages, fluently recall entire books from memory. By every measure, he was the most intelligent human of his generation. He died at 53. Most of his work became obsolete within 2 decades. His contributions, while real, didn't reshape their fields. Feynman had IQ 125, merely above average. Good, not exceptional. He died at 69. His work defines physics education 40 years after his death. His diagrams remain the standard method. His lectures remain the standard pedagogy. His approach to thinking remains the model for how science should be practiced, not because he was smarter, because he thought better. Freeman Dyson, a physicist who knew both men, wrote that Feynman's genius wasn't intellectual horsepower. It was the power to see things simply, to strip away unnecessary complications and get to the heart of the matter. This power came from method, not genetics. The system worships IQ because IQ is easy to measure. Tests need scalability. Institutions need sorting mechanisms, credentials. It's signal intelligence because employers need hiring shortcuts. This entire apparatus optimizes for speed, fast pattern matching, quick recall, rapid processing. But reality doesn't care about speed. Reality rewards understanding. In his final years, Feynman wrote on his Caltech blackboard, "What I cannot create, I do not understand." This sentence contains his entire method. Understanding means ability to reconstruct from nothing. If you can't build it from first principles, you don't understand it. You've only memorized someone else's understanding. You don't need a high IQ to practice this method. You need patience to think slower, humility to choose boring problems that teach fundamentals, discipline to simplify until clarity emerges. These are practices, not gifts. Learnable, improvable, systematic. The education system will never teach this because education optimizes for credential production, not understanding cultivation. Schools need grades, tests, rankings. This requires speed and standardization. Feynman's method is slow and individualized. It doesn't scale to classroom management. It doesn't produce neat percentile rankings. But for individuals learning on their own terms, it's available completely. When you study technical documentation, resist the urge to copy-paste code examples. Reconstruct the logic yourself from first principles. When you prepare for career transitions, avoid chasing impressive titles. Choose projects that teach complete systems, even if they seem tedious. When you explain your expertise, simplify relentlessly until non-experts understand. If you can't draw it simply, you don't truly understand it yet. Think slower. You'll understand deeper. Over years, depth beats speed every time. Over decades, method beats genetics consistently. Feynman proved this across 50 years of physics. His 125 IQ didn't limit him. It liberated him. Without the arrogance that fast intelligence produces, he stayed curious about basic questions. Without the credential addiction that high achievers suffer, he chose learning over status. Without the complexity trap that geniuses fall into, he simplified until truth emerged visible to everyone. This is available to you, not genetic gifts, not standardized test scores, not prestigious degrees. Just method, reconstruct concepts from scratch until you can build them yourself. Choose boring problems that others avoid because they teach foundational systems. Simplify relentlessly until you can explain ideas so clearly that beginners grasp them immediately. The path is slow, the results compound, and intelligence, it turns out, is less about the brain you were born with and more about the method you practice daily. You spent 3 hours yesterday learning something important. This morning, you can barely remember the main points. By next week, it'll be gone completely. This isn't a focus problem. It's not age. And it's not because you're not smart enough. In 1951, a 33-year-old physicist named Richard Feynman accepted a teaching position in Brazil. He walked into classrooms at the Centro Brasileiro de Pesquisas Físicas expecting eager students. What he discovered instead was a learning catastrophe so complete, so universal, that it explains why your brain is deleting everything you're trying to learn right now. This comes from Feynman's documented account in Surely You're Joking, Mr. Feynman? The mechanism he uncovered doesn't just explain forgetting. It reveals the invisible difference between people who retain knowledge for life and people who pass exams but remember nothing. By the end of this, you'll know exactly why your brain betrays you. More importantly, you'll have the specific method Feynman used to make knowledge permanent. The story begins with Feynman stepping off a plane in Rio de Janeiro. He'd been invited to teach physics for a year. These were serious students at a prestigious institution. They attended lectures, they took notes, they studied textbooks, they passed exams with high marks. Feynman's first few lectures went smoothly. Students nodded. They asked questions using the right terminology. Everything seemed normal. Then Feynman did something unusual. During a lecture on polarized light, he asked a student to explain what they'd learned the previous week about Brewster's angle. The student stood up and recited perfectly. Brewster's angle is the angle at which light reflected from a surface is completely polarized. Textbook perfect, word for word. Feynman asked, "What does that mean?" Silence. He tried again. "Can you give me an example? What surface? What would I see?" The student looked confused. Other students shifted uncomfortably. Nobody could answer. They had memorized the definition flawlessly. They could recite it under exam conditions, but they had no idea what it meant. You've done this. You memorized formulas for calculus, but couldn't explain why integration works. You learned accounting principles, but panic when someone asks you to apply them to a real scenario. You read that business book everyone praised, highlighted passages, then couldn't summarize the core idea a month later. Your brain stored the words perfectly. It deleted the understanding completely. Feynman started testing this systematically. He'd ask students to explain concepts in different words, to apply principles to new situations, to describe what they'd actually see if they performed an experiment. Same result every time. Perfect recitation, zero comprehension. But here's where it gets worse. These students had spent years in this system. They'd passed hundreds of exams, they had credentials, they looked educated, but Feynman discovered they couldn't answer a single question that required actual thinking. He found textbooks where students had underlined passages. When he looked closer, he realized they were memorizing which sentences to underline based on previous exams, not because they understood why those sentences mattered. One textbook chapter started, "Triboluminescence is the phenomenon where light is emitted when crystals are crushed." Students had this memorized. Feynman asked if anyone could name one substance that was triboluminescent. Nobody knew. The textbook never mentioned actual crystals, just the word crystals in abstract. These students could define triboluminescence perfectly. They just had no connection to reality. The same principle destroys your retention today. You attend that conference, take notes on key frameworks, then can't remember a single actionable insight 3 days later. You complete that online course, get the certificate, then freeze when someone asks you to actually use what you learned. Your brain is doing exactly what those Brazilian students' brains did. It's storing symbols without connecting them to meaning. Feynman was baffled. How could an entire educational system produce this result? Then he attended other professors' lectures. He watched how they taught. He examined their textbooks more carefully. He discovered something disturbing. The professors were teaching the same way they'd been taught. They'd lecture about dielectric polarization without ever explaining what a dielectric was or why anyone cared. They'd write equations on blackboards without connecting them to anything students could see or touch. Students copied these equations. They memorized them. They reproduced them on exams. But the equations were just shapes on paper, disconnected from physical reality. Feynman called this cargo cult science in his later Caltech commencement address. The students had the appearance of learning, the notebooks, the terminology, the exam scores, but none of the substance. Like cargo cult members building fake airstrips hoping planes would land, these students were going through learning motions, hoping knowledge would appear. It never did. This explains why you forget. Your brain doesn't delete information randomly. It deletes information that has no connections. When you learn something as isolated words, blockchain is a distributed ledger technology, your brain has nowhere to store it except as a string of syllables. There's no web of meaning, no connection to things you already understand, no link to situations where you'd use it. So your brain does what it's designed to do. It assumes this information doesn't matter and deletes it to make room for things that do. The students in Brazil could pass exams because exams tested recitation, but the knowledge evaporated immediately because it was never connected to anything real. You've experienced this exact pattern. You crammed for that certification exam, passed with a good score, then couldn't answer basic questions about the material 2 months later. Not because you're forgetful, because you learned words without weaving them into your existing knowledge structure. Feynman discovered the mechanism. Now, here's what he did about it. He started teaching differently. Instead of defining terms, he'd describe phenomena first. Instead of equations, he'd start with observations anyone could make. For polarized light, he didn't begin with Brewster's angle. He started by asking, what happens when you look at a lake on a sunny day wearing polarized sunglasses? Why does glare disappear when you turn your head? Students could visualize this. They'd seen it. Now they had a hook. Then he'd explain. Light waves vibrate in different directions. Water surfaces reflect waves vibrating horizontally more than vertically. Your sunglasses block horizontal vibrations. That's why glare disappears. Same physics, completely different approach. He started with something concrete, something connected to experience, then built up to the technical term. Students started understanding, not memorizing, understanding. Feynman later refined this into what's now called the Feynman technique. The principle is simple. If you can't explain something in simple language, you don't understand it. Not simple as in dumbed down. Simple as in connected to things anyone can grasp. This is why you forget most books you read. You highlight impressive-sounding sentences, but never stop to translate them into your own words, connected to your own experience. The highlights sit there, disconnected, until your brain sweeps them away. This is why you forget most courses you take. The instructor presents frameworks and models, you copy them down, but you never build the bridge between those abstractions and your actual work. Your brain is doing its job. It's eliminating noise. The problem is, your learning method makes everything look like noise. But there's a deeper issue Feynman uncovered in Brazil. He noticed something strange about which students struggled most. The students who'd spent the most time studying, the ones with the most notes, the most underlines, the most hours logged, often performed worst on his understanding tests. They'd been reinforcing the wrong thing. Every hour spent memorizing disconnected facts was an hour spent teaching their brain that this is what learning looked like. They'd built a skill, just the wrong skill, the skill of recitation without comprehension. You've built this skill too. Years of education trained you to do it. Highlight key passages, copy down important points, memorize definitions, reproduce them under test conditions. This worked in school because school mostly tested recitation. But in your career, nobody cares if you can recite. They care if you can apply, adapt, synthesize, explain. And your brain, trained for decades to store disconnected words, keeps doing what it learned to do. Feynman saw this pattern everywhere once he started looking. Students who could recite Maxwell's equations but couldn't explain why a radio worked. Students who'd memorized thermodynamic laws but couldn't predict whether ice would melt faster in a vacuum. The words were there. The understanding was absent. This is why you can read 3 books on leadership and still freeze in your first management situation. You memorize the principles, provide clear feedback, build trust, delegate effectively. But you never connected them to specific moments, specific challenges, specific conversations. So, when the moment comes, your brain searches for relevant knowledge and finds words, just words. And words don't tell you what to do. Feynman documented his Brazilian experience as a warning, but he also provided the solution. The solution isn't studying harder, it's studying differently. After returning from Brazil, Feynman developed a teaching philosophy he used at Caltech for decades. His lecture series, now published as The Feynman Lectures on Physics, demonstrates the principle in action. He never started with equations. He started with questions anyone could ask. Why is the sky blue? Why does ice float? How does a magnet work? Then he'd build understanding layer by layer, each layer connected to the previous one, each layer testable against experience. His students didn't just pass exams. They retained knowledge for life, because that knowledge was woven into a web of meaning, not stored as isolated facts. Here's what this means for everything you're trying to learn right now. You're probably learning backwards. You're starting with conclusions, the frameworks, the models, the definitions, and trying to memorize them. This is why they disappear. Reverse the process. Start with the problem the knowledge solves. Start with the question it answers. Start with the phenomenon it explains. Before you read another page of that technical book, ask, what real situation would make me need this information? Before you take notes in that workshop, ask, what specific problem at work would this solve? Then, and only then, learn the content. But learn it as the answer to that question, not as isolated information. This is what Feynman did instinctively. It's why he could explain quantum electrodynamics to non-physicists. He never memorized disconnected equations. He built each piece of knowledge onto a foundation of understanding connected to things he could see and test and verify. But there's a second critical step. Feynman's technique requires you to explain what you learned in your own words, as if teaching someone with no background, not summarizing, not paraphrasing. Explaining from scratch, using only concepts and words your listener already knows. When you try this, something remarkable happens. You instantly discover the gaps. You'll start explaining, hit a point where you realize you can't actually describe what happens next, and discover you memorize that part without understanding it. This is the moment of truth. Most people panic here. They think, I should have understood this. I'm not smart enough. Wrong diagnosis. You found the disconnect before it became permanent. Now you can go back and build the actual connection. Feynman did this constantly. In his documented conversations with colleagues, he'd explain ideas using everyday analogies. When the analogy broke down, he knew he'd hit a boundary of his understanding. He'd say, I don't actually understand that part yet. Then he'd go figure it out. This habit, explaining in simple terms, finding the gaps, filling them, is why Feynman retained knowledge that others with similar intelligence forgot. The mechanism is simple. Your brain remembers information woven into a connected structure. It deletes information stored as isolated units. So, here's your system, starting Monday morning. Pick something you're trying to learn right now. A book, a course, a skill for work. Before you consume more content, stop and ask, what problem does this solve? Write down a specific scenario where you'd use this knowledge. Make it concrete. Not, I'll use this for better decision making. Instead, I'll use this next time I have to choose between 2 job offers. Now, as you learn, constantly test comprehension. After each section, close the book and explain it out loud to an imaginary person who knows nothing about this topic. Use only words they'd understand. No jargon unless you define it in their terms first. If you need to say quantum superposition, explain it as the particle exists in multiple states at once, like a coin spinning in the air being both heads and tails until it lands. When you hit a part you can't explain simply, stop. Don't move forward. That's the disconnect. That's the part your brain will delete next week. Go back to the source. Read it again. But this time, build the bridge. Connect it to something you already understand. Find the analogy. Describe what you'd see, hear, feel if you encountered this in real life. Only when you can explain it, simply do you move on. This feels slower than highlighting and note-taking. It is slower, but highlighting is fake progress. You're moving through pages without learning anything that lasts. Feynman's method is real progress. You're moving through less content, but you're actually learning it permanently. 3 months from now, test yourself. With the highlighting method, you'll remember almost nothing. With Feynman's method, you'll be able to explain the core concepts without reviewing, because they're not stored as words anymore. They're woven into your understanding of how things work. There's one more documented insight from Feynman's Brazil experience that changes everything. Near the end of his year there, he gave a lecture to the faculty about what he'd observed. He explained the problem, students memorizing without understanding. He showed them the evidence. Perfect recitation, 0. Application? The faculty agreed completely. They nodded. They said yes, this is a serious problem. They thanked him for identifying it. Then they went right back to teaching the same way. Feynman realized something crucial. The faculty had memorized his critique without understanding it either. They could recite his concerns. They just couldn't connect them to their own behavior. This is the meta lesson. Knowing about the problem doesn't fix it. You can read this entire script, understand intellectually why you forget things, and still not change your learning method. Because understanding intellectually and understanding in your bones are different things. You need to experience the technique working. You need to try explaining something you know and feel the moment you hit the gap. You need to fill that gap and feel the difference between words you memorized and concepts you actually understand. That experience is what changes behavior, not the intellectual knowledge that you should change. So here's your single action step. Tomorrow, take something you learned recently, anything, a chapter from a book, a concept from a course, a skill you're developing. Sit down with a blank page, no notes, no references, just your memory. Try to explain it to someone who knows nothing about the topic. Write it out or say it out loud. Use only words they'd understand. You'll hit the gaps within minutes. Those gaps are what your brain is about to delete. Now, go back to the source. But this time, build the bridge. Connect the concept to something concrete. Find the analogy, make it real, then try explaining again. Keep cycling until you can do the entire explanation without gaps, using only simple language. This one exercise will reveal more about your learning gaps than a month of highlighting and note-taking, and it will teach you in your bones the difference between memorizing and understanding. Feynman spent his career proving a simple truth. If you can't explain it simply, you don't understand it yet. Not, you're not smart enough. Not, it's too complicated. You just haven't built the connections yet. Your brain isn't failing you. It's doing exactly what it's supposed to do, discarding disconnected information to make room for knowledge that actually matters. The question is, are you giving it knowledge or just feeding it words?
These are just blocks, simple shapes, colors, a child's toy. But you, an educated adult with years of schooling, you can't do what a 3-year-old does naturally with these. You can't look at these blocks and immediately see the hundreds of different structures you could build. You can't pick them up and start creating without fear, without planning, without worrying if you're doing it right. A child can. A child sees these blocks and immediately starts building, experimenting, playing, creating. No self-doubt, no performance anxiety, no voice in their head saying, "I'm not good at this." I also put blocks down. What happened to you? What happened between being that fearless 3-year-old and becoming the adult you are now? I'll direct address. You got educated. You got taught. You spent years in a system that told you learning works a certain way. That intelligence looks a certain way. That being smart means memorizing facts, following procedures, getting right answers on tests. And that system lied to you. It taught you wrong. And in the process, it convinced you that you're not as smart as you actually are. Lean in F today. I'm going to prove to you that you're smarter than you think. Not with empty motivation, not with feel-good platitudes, with evidence, with examples. With the story of how Richard Feynman discovered that most people dramatically underestimate their own intelligence because they've been taught to measure it in completely the wrong ways. And I'm going to show you what real intelligence looks like, what real learning looks like, and why the version you were taught in school has almost nothing to do with actual human capability. I walk across stage. Let me start with a story. This story is going to challenge everything you believe about intelligence. It's the 1960s. Feynman is teaching at Caltech, and a student comes to him, frustrated. "Professor Feynman, I just don't understand quantum mechanics. I've tried. I've studied. But I think I'm just not smart enough for this." And Feynman looks at him and says something that shocks the student. "No one understands quantum mechanics." Pause 8, the student is confused. "But you understand it. You won the Nobel Prize for it." And Feynman says, "I don't understand it the way you think understanding means. I can work with it. I can predict what will happen. I can use the mathematics. But the deep why, nobody knows. Nobody understands, not me, not Einstein. Nobody make the point." And then Feynman says something even more important. The problem isn't that you're not smart enough. The problem is that you think understanding means something it doesn't mean. You think being smart means having all the answers. It doesn't. Being smart means asking good questions and being comfortable not knowing the answers. Hey, let that land. That student thought he wasn't smart enough. But the real problem was he'd been taught wrong. He'd been taught that intelligence means certainty, complete understanding, having all the answers. So when he encountered something he didn't fully understand, he concluded, "I must not be smart." I direct addressee. That's you too. That's all of us. We've been taught wrong about what intelligence is, what capability is, what it means to be smart. And because we've been taught wrong, we've been measuring ourselves with the wrong ruler and concluding, incorrectly, that we're not intelligent. Let her get intense. Let me show you exactly how you were taught wrong. The specific ways the education system gave you false ideas about intelligence that have been limiting you ever since. Because once you see how you were taught wrong, you'll see how smart you actually are. A first false teaching number 1. Intelligence is about memorization. This is everywhere in traditional education. Tests measure how much you memorized. Grades reward how many facts you retained. Success means recalling information on demand. And if you struggle with memorization, if you forget things, if you need to look things up, you're labeled as not smart. But that's completely wrong. Memorization has almost nothing to do with intelligence. A for share Feynman example. Feynman forgot things constantly. Phone numbers, dates, names. Even physics formulas he'd used 100 times. He'd have to derive them again from first principles. Did that make him less intelligent? No, it made him more intelligent. Because instead of cluttering his mind with memorized facts, he understood the underlying principles so deeply that he could reconstruct anything he needed. Hacks make the distinction. Memorization is storage. Intelligence is processing. A computer has perfect memorization. It can store billions of facts flawlessly. Is a computer intelligent? No, because storage without understanding isn't intelligence. Give analogy. Think of it this way. Having a library in your house doesn't make you knowledgeable. Being able to use the library, to find what you need, to connect ideas, to synthesize information, that's intelligence. Your education system measured how many books you memorized. But intelligence is about how well you can use information, not how much you've stored. Osaka, make it personal here. So if you struggle with memorization, if you forget names, dates, facts, that doesn't mean you're not intelligent. It might actually mean you're using your cognitive resources for something more valuable: understanding, connection. Synthesis, or second false teaching. A false teaching number 2, intelligence, is about speed. This one damages people deeply. Tests are timed. Speed reading is praised. Thinking fast is equated with being smart, and thinking slowly, that's labeled as dull, slow-witted, less intelligent, but this is backwards. Completely backwards. Share research. Psychologists have studied this. They found that the deepest thinking, the most creative insights, the most profound understanding, it all comes from slow thinking, from taking time, from sitting with problems. Fast thinking is pattern matching. It's using existing knowledge to quickly recognize familiar situations. Useful, yes, but not deep intelligence. Slow thinking is actual reasoning. It's building new understanding. It's seeing connections others miss. That's real intelligence. To share Feynman example, Feynman was not fast. When presented with a problem, he didn't immediately know the answer. He'd think, slowly, deeply, sometimes for days or weeks. Other physicists would solve standard problems faster than him because they'd memorized the techniques, they'd pattern match. Quick, efficient. But Feynman would solve problems they couldn't solve at all because he was thinking deeply, not quickly. Understanding fundamentally, not just pattern matching. I make the point, speed is not intelligence. Speed is practiced pattern recognition. Intelligence is the ability to think deeply about novel situations. Make it personal. So if you're a slow thinker, if you need time to process, time to understand, time to see connections, that's not a deficit. That's deep intelligence. That's real thinking. The education system penalized you for it. Time tests, pressure to answer quickly, praise for students who raise their hands first. But outside of school, in real life, the slow, deep thinkers are the ones who solve the hard problems, who have the insights, who create breakthroughs. Third false teaching number 3, intelligence is about getting right answers. This is the most damaging one. School trains you, there's a right answer. Your job is to find it. If you get it wrong, you fail. You're marked down. You're told you're incorrect. Get passionate. And this creates a devastating mindset. Being wrong is bad. Making mistakes is failure. Not knowing is shameful. So you learn to avoid situations where you might be wrong. You don't take risks. You don't explore. You don't guess. You wait until you're certain before you answer. Pauses, and that obliterates intelligence. Real intelligence. Creative intelligence. The kind that leads to discovery and insight and innovation. A share Feynman insight, and Feynman said, I learned very early that there's a big difference between knowing the name of something and knowing something. School taught you to know names, right answers, correct responses. But real intelligence is about knowing things, understanding them, being able to reason about them. And that requires being wrong a lot, making mistakes, testing ideas, discovering where your understanding breaks down. Sepan give example, a child learning to walk falls hundreds of times. Each fall is information. Each mistake teaches balance. Each wrong attempt leads toward the right one. We don't say the child is failing. We say the child is learning. But school taught you wrong answers are failures. Mistakes are deficits. Not knowing is shameful. I make the points that's backwards. Being wrong is learning. Making mistakes is intelligence in action. Not knowing is the starting point of understanding. Estemki, make it personal. So if you're afraid of being wrong, if you hesitate to try things because you might fail, that's not because you're not intelligent. That's because you were taught wrong. You were taught that intelligence means always being right. But real intelligence means being willing to be wrong in pursuit of understanding. Fourth false teaching number 4. Intelligence is demonstrated through performance. School measures intelligence through tests, through grades, through your ability to perform on demand under pressure. Can you recall facts under time pressure? Can you solve standard problems in test conditions? Can you demonstrate knowledge in artificial settings, act pauses? But that's not how intelligence works in real life. That's not how creativity works. That's not how problem solving works. Share contrast, real intelligence looks like this. You encounter a problem you've never seen before. You don't know the answer. There is no answer yet. You have to figure it out. You have time, you have resources, you can research, you can experiment, you can think, you can fail and try again. That's real-world intelligence. And it looks nothing like test taking. Share Feynman examples. Feynman worked on some problems for years. No time limit, no pressure to perform. Just persistent curiosity and willingness to not know. The Challenger investigation. He spent weeks investigating, asking questions, testing hypotheses, making mistakes, revising his understanding. That's real intelligence. That's how problems actually get solved. Make the point. But school taught you that intelligence means performing on demand, in time conditions, with no resources, under pressure. So if you struggle with performance pressure, if your mind goes blank during tests, if you freeze during timed exams, if you need time and space to think, that doesn't mean you're not intelligent. That means you're a real-world thinker, not a test taker. And real-world thinking is what actually matters. Fifth false teaching error, false teaching number 5, intelligence is general and fixed. This is the most insidious one. School sorts people smart students, average students, below average students. And these labels stick. They become identities. I'm just not a math person. I'm not good at writing. I'm not smart enough for science. Right? Get intense. These statements are lies. Lies you were taught. Lies you internalized. Lies that have been limiting you for years. Share the truth. Intelligence isn't general. You're not smart or not smart. You have different capabilities in different domains. You might be brilliant at spatial reasoning and struggle with abstract logic. Brilliant at language and struggle with numbers. Brilliant at understanding people and struggle with understanding systems. That's not about being smart or dumb. That's about having different cognitive strengths. Share Feynman. Example of Feynman was a Nobel Prize winning physicist. Brilliant at mathematical reasoning. And he struggled with some things that came easily to others. He struggled with certain kinds of memory tasks, with facial recognition, with social conventions, with administrative work. Did that make him less intelligent? No. It meant his intelligence was concentrated in certain areas and not others. Make the point, and intelligence isn't fixed. It develops, it grows, it improves with use. When you practice something, you get better at it. Not because you became smarter, because you developed specific capabilities through use. Share research or neuroscientists have proven this. Your brain physically changes based on what you practice. Neural pathways strengthen, new connections form, capabilities develop. This happens at any age. Childadults, elderly. The brain remains plastic, changeable, growable. Make it personally. So when you say, I'm just not smart enough for this, you're wrong. You might not have developed that specific capability yet, but you can through practice, through effort, through time. You're not fixed. You're not limited. You're capable of developing whatever intelligence you choose to develop, or bring it all together. So those are the 5 false teachings. Intelligence is about memorization. No, it's about understanding. Intelligence is about speed. No, it's about depth. Intelligence is about being right. No, it's about being willing to be wrong. Intelligence is about performance. No, it's about real-world problem solving. Intelligence is fixed. So no, it's developable. Pavaz, you were taught all 5 of these lies, and you measured yourself against these false standards, and concluded, I'm not that smart. Acts a direct statement, but you are. You're smarter than you think. You were just taught wrong. Most never share what real intelligence looks like. Let me show you what real intelligence actually looks like. Using Feynman's definition. Using what actually matters in the real world. Real intelligence is the ability to figure things out. That's it. That's the definition. Can you encounter something new, something unfamiliar, something you don't currently understand and figure it out? How can I make it concrete? No. Do you already know it? Not can you recall it, call it from memory. Not can you recognize it and apply a memorized pattern. But can you figure it out? Can you reason about it? Can you experiment and learn? Can you go from not understanding to understanding? Avar share examples. A child figuring out how to stack blocks so they don't fall. That's intelligence. An adult figuring out how to fix a broken appliance by observing how it works. That's intelligence. Someone figuring out how to navigate a new city by noticing patterns and testing hypotheses. That's intelligence. And make the point, and you do this all the time. Every day. In ways you don't even notice. In ways school never measured or valued. You figure out how to use new software, how to cook a new recipe, how to solve problems at work, how to understand people, how to navigate complex situations. Get passionate! That's intelligence! Real intelligence! The kind that actually matters! But school never measured that. School measured whether you could memorize and recall, whether you could pattern match quickly, whether you could perform under pressure. Don't pause these. So you developed real intelligence, the ability to figure things out, and simultaneously believed you weren't smart, because school measured the wrong things. Jiv the method. So how do you reclaim your intelligence? How do you start seeing yourself as the capable, intelligent person you actually are? By redefining what counts. By measuring yourself against the right standards instead of the false ones. SM present new measurement. Here's the new measurement. Ask yourself these questions. Question 1. When I encounter something new, do I eventually figure it out? Not immediately, not without effort. But eventually, do I figure things out? If yes, you're intelligent. That's the definition. That's what matters. Question 2. When I make mistakes, do I learn from them? Do I update my understanding? Do I get better? If yes, you're intelligent. That's learning. That's growth. That's real cognitive capability. Question 3. When I don't know something, am I able to ask good questions, to investigate, to seek understanding? If yes, you're intelligent. That's curiosity. That's the foundation of all learning and discovery. Question 4. When I understand something, can I explain it to someone else? Can I make it simple? Can I connect it to other things? If yes, you're intelligent. That's deep understanding. That's real mastery. Question 5. When I need to solve a problem, can I try different approaches? Can I experiment? Can I persist even when it's difficult? If yes, you're intelligent. That's creativity. That's resilience. That's problem-solving capability. The Zarvern make the point. Those 5 questions measure real intelligence. The intelligence that matters. The intelligence you actually have. School never measured those. School measured memorization, speed, performance, and right answers. So you've been measuring yourself wrong your entire life. Share transformation story. Let me tell you about someone who discovered this. Call him Tom. Tom believed he wasn't smart. He'd struggled in school. Average grades. Never felt like he got it as quickly as other students. Believed he was intellectually limited. And he carried that belief into adulthood. Didn't pursue ambitious careers. Didn't take on challenges. Played it safe because he wasn't smart enough for anything more. Far as the turning point, then something happened at work. A complex problem. Something nobody knew how to solve, including the smart people, the ones with good grades and advanced degrees. And Tom figured it out, slowly, through experimentation, through trial and error, through persistent curiosity. He didn't know the answer, he figured it out. And his solution worked at the realization. And that's when it hit him. Wait, I'm intelligent. I just solved something the smart people couldn't solve. Maybe I'm smarter than I thought. So he started paying attention. Started noticing all the ways he figured things out, solved problems, learned new skills, understood complex situations. And he realized he did this all the time. He was doing intelligent things constantly. Real intelligence. The kind that actually matters. The transformation, he just hadn't been measuring it. Hadn't been noticing it, because he was still measuring himself by school standards, memorization, speed, test performance. Once he started measuring real intelligence, the ability to figure things out, he saw he was extremely intelligent, always had been. He'd just been taught wrong about what intelligence means. Have the result 5 years later, Tom has a completely different career. More ambitious, more challenging, more successful, not because he became smarter, but because he recognized the intelligence he already had and stopped limiting himself based on false measurements. Make it personal feat. This is you too. You're doing intelligent things constantly, figuring things out, learning, adapting, problem solving. You just haven't been noticing it, haven't been valuing it, because you're still measuring yourself against school standards. Direct challenge he's. So here's what I want you to do, starting today. Notice your intelligence. Actually pay attention to it. When you figure something out, anything, acknowledge it. I figured that out. That's intelligence. When you learn something new, anything, acknowledge it. I learned that. That's capability. When you solve a problem, any problem, acknowledge it. I solved that. That's real-world intelligence. Ace, continue P. Keep a list for 1 week. Every time you do something intelligent, by the real definition, not the school definition, write it down. Figured out why my computer wasn't working. Learned how to use that new feature. Solved that conflict with my colleague. Understood that complex concept. Navigated that difficult situation. Ash, make the promise. At the end of that week, you'll have a list of dozens of examples of your intelligence. Real intelligence, the kind that actually matters. And you'll start seeing yourself differently. Not as someone who's not smart enough, but as someone who figures things out. Who learns, who grows, who's intelligent in the ways that actually count. Arcert jet philosophical fee. Here's what Feynman understood that most people missed: everyone is intelligent. Everyone has the capacity to figure things out. Everyone can learn. Everyone can understand. The difference isn't in capability. It's in what you've been taught to value, what you've been taught to measure. What you've been taught counts as intelligence. Make the point your school taught you wrong. It taught you that intelligence is memorization, speed, performance, and right answers. So you measured yourself against those standards. And many of you concluded, I'm not smart. Revealed the truth you saw, but you are. You're extremely intelligent. You're constantly doing intelligent things. You're figuring things out every single day. You just haven't been measuring it, haven't been noticing it, haven't been valuing it. Now for final stories, let me end with one more Feynman story. This one shows everything. A journalist asks Feynman, Professor Feynman, you're clearly much smarter than the average person. What makes you so intelligent? And Feynman says, I'm not smarter. I just know how to think. I know how to ask questions. I know how to admit when I don't know something. I know how to figure things out. The journalist is confused. But those are things anyone can do. And Feynman smiles.
Exactly.
Make the final point: intelligence isn't rare. It isn't special. It isn't limited to a few people with high test scores. Intelligence is figuring things out. And everyone can do that. Everyone does do that. Including you. You're smarter than you think. You've always been smart. You were just taught wrong about what intelligence means. Walk to center. So stop measuring yourself against school standards. Stop believing you're not a math person, or not smart enough, or not capable of understanding complex things. Those beliefs are based on false measurements, on wrong definitions, on lies you were taught. Fact, direct statement, measure yourself by what matters. Can you figure things out? Can you learn? Can you grow? If yes, and it is yes, then you're intelligent, really intelligent, in the ways that actually count. Final challenge this week: notice your intelligence. Value it, acknowledge it, build confidence in it, because you're smarter than you think. You always have been. You were just taught wrong. But Smila, now you know better. Now you can measure yourself correctly. Now you can see your intelligence for what it really is. Thank you. Ace Betude, if you want to understand more about how Feynman thought about intelligence, learning, and capability, if you want to develop your own intelligence using his methods, do me a favor. Like this video and subscribe to the Mind of Richard Feynman channel. We're exploring what real intelligence looks like, what real learning looks like, how to develop real capability, not based on school standards, but on what actually matters. Join us. Let's reclaim our intelligence together. See you in the next one.